Good morning to all the Iasta delegates and invitees. It is with great pleasure that we gather here today to inaugurate Iasta National Conference 2023. Iasta, since its foundation, has worked in the direction to provide platform to aerosol researchers, technocrats, policymakers, students, and to share expertise and knowledge. And Iasta conferences have always received a great deal of attention. Similar to previous occasions, we are gathered here with the same excitement and anticipation for the coming 3 days. Today marks the beginning of a journey filled with intellectual discourse, collaborative endeavor, and showcase of technology with the pursuit of excellence. To begin with the inaugural program, I would like to invite dignitaries to the dais. Padma Shri Dr. R.B. Grover, the chief guest of this event, Dr. D.K. Aswal, Director Health Safety and Environment Group, BARC, our guest of honor, our keynote speaker for the event, Professor Sotiris Pratsinis from Swiss Federal Institute of Technology, Zurich, Switzerland. I request Dr. S.N. Tripathi, President Iasta, and Dr. B.K. Sapra, Member National Organizing Committee, to accompany the guests to the dais. We would like to welcome the guests on the dais with floral bouquets. I would request Srimati Amruta to present Dr. R.B. Grover a flower bouquet. Now I would request Srimati Sheetal Johnson to gift a bouquet of flowers to Dr. Pratsinis. Now I would request Srimati Rajeshwari to greet Dr. D.K. Aswal with a bouquet of flowers. I would request Mr. Jalal to hand over Dr. S.N. Tripathi with a bouquet of flowers. Thanks, Jalal. I would now request Srimati Rama Prajit to present a bouquet of flowers to Dr. B.K. Sapra. Thank you, Rama. Thank you. I would now invite Dr. B.K. Sapra, Head Radiological Physics and Advisory Division, Baba Atomic Research Center, and a member of National Organizing Committee, who has guided us day in and day out for this event, to deliver a welcome address. Ma'am, please.
So, very good morning to all of you, and dear esteemed dignitaries on the dais here with us, and all the participants of Iasta 2023. So, let me begin by welcoming and congratulating the new Iasta team. As you all are aware, we had elections, and in 2023 we have a new team who has started with this conference under the presidency of Dr. S.N. Tripathi from IIT Kanpur. And these elections, as you all know, were long due. And finally, now we have a young team to take over the activities with new ideas and directions. So I join with the president of Iasta, Dr. S.N. Tripathi, in extending a warm welcome to each one of you here. So we are having this conference almost after 5 years. The last one we had was in 2018. And as we all know, that Iasta, since its foundation, has worked in the direction to provide platform to aerosol researchers. We have seen our colleagues here from various institutes grow in status, grow in their research activities, and it's always a pleasure because we are a very small community, and I think almost all of us know each other very well. So it's nice to see how the aerosol research has progressed in India. And as we begin this event, it is our great pleasure and good fortune to have in our midst the chief guest for this event, an eminent personality, Padma Shri Dr. R.B. Grover. He has been one of the key shapers of the nuclear energy program of India, and his expertise encompasses the mix of technical excellence, academics, as well as policy framing. In addition to his responsibilities as member Atomic Energy Commission, Dr. Grover dedicates a significant amount of his time and efforts in guiding students even till date and motivating them to take up studies related to technico-legal aspects that will be useful for better policy framework. We are very thankful and welcome to you, sir. Warm greetings also to Dr. D.K. Aswal, Director, Health, Safety and Environment Group of BRC, who has always been a source of motivation and guidance in all respects. He has been overseeing the organization of this conference very well. It's a memorable day for us because we have Dr. Pratsin amidst us to give us the keynote address. And as I was telling him, we have heard of his papers, we have heard of his work right from the day we joined. So it's a pleasure to finally see him. And he has a lot of his work is dedicated towards the combustion aerosols, flame synthesis, soot, etc., characterization. And all of us at some stage of our professional career would have gone through his work. And a warm welcome to you, sir, in India. I hope you are having a good time here. I also welcome our esteemed invited speakers and presenters who have worked tirelessly to share their expertise and their research findings. The diverse topics that are covered in this conference reflect the multifaceted nature of this subject. I also acknowledge the support of all the sponsors and our trade partners, and I would urge that all of you, please, whenever you are having time during the tea time, lunch time, or otherwise, please go and have a look at the technologies that they have on display outside. I'm sure they will be helpful for your research as you go along. And a huge welcome to all the registered participants here. And I think we have got about 300 registrations, that is what I heard. And I'm sure that our organizing team must have taken good care of you, ensuring that your travel and stay is comfortable. And please feel free to talk to the organizing team in case you have any issues. The scientific team also has put together very interesting events such as the lightning sessions and panel discussions. I hope that all of you actively participate, ask questions, and engage in meaningful conversations. So, dear friends, the success of such events always depends on the shared expertise and enthusiasm of the participants. So let us take this opportunity to learn from each other, make new connections, collaborate towards a shared vision of advancing this subject. So with that, welcome to all of you, and thank you.
Thank you, Dr. B.K. Sapra. Indian Aerosol Science and Technology Association, Iasta members, are distinguished, and they have earned respect and place on the national and international level always. It's a matter of utmost pride to us that Professor S.N. Tripathi, who is currently the President of India, has been awarded with Infosys Award this year. I would now request Professor S.N. Tripathi to deliver his presidential address on this platform. Sir, please.
Professor Grover, Dr. Aswal, Professor Prasnis, Dr. Sapra, and all the delegates who have come from every part of India and abroad. I joined Dr. Sapra to welcome you to the conference in Mumbai, particularly Professor Grover, who could spare some time to come here and bless this occasion. Most of the things I wanted to say has been said by Dr. Sapra. So you already know mostly what Iasta is all about. I just would add a couple of things here. That this society, as you know, mainly works to further aerosol engineering, science and technology in India, has been founded in 1988, I think, in BRC. So you see it's now 35 years old, mature society. This conference, of course, is happening after 5 years because of 3 years were washed out by COVID-19. And as Dr. Sapra was telling that is curated quite well. We have changed the format a little bit, and we have done some things here and there. There are new panels and all that there, right? And there was a pretty, I would say, enthusiastic response from within India and outside, because we have received about 300 abstracts, and I believe at least there will be altogether 100 plus oral, poster, and all kind of presentations that would be made in next 3 days. So that all sounds quite good. I will just take this occasion also to reflect on Indian contribution to aerosol science and technology in the global arena. So I was, just before coming, I was looking into that what's the Indian contribution to the most impactful journals, right? For example, I just took Nature, Science, Proceedings of National Academy of Sciences, Nature Sustainability, Nature Nanotechnology, Nature Geoscience, and Nature Communications. So we know that we put it together, they are, and Science Advances, they are probably the highest impact journals. If you take away maybe some of the very top cited or having impact factor journals like Lancet, etc. So last 5 years, we had about 550 papers that came out in these 7 or 8 odd journals. And we had contributed total in 15. So 15 out of 550, which just makes us like a 2% contribution in the top most journals. And I did this search with aerosol in the title. And if you compare that with the Chinese and American contributions, that is about 25 and 42%. So this is a pretty large gap, you see, 2% with respect to 25 and 42% over the last 5 years. And if you look at number of patents, which is a good measure of the technologies which are being produced, and again, I did this search. I got some help from our incubation center. So that data was not available for US, but that is there for India and China. And China has registered just about 19,000 patents in the last 5 years. And India has about something like 2,800. So that's 1/6. So that the gap what we see earlier between the number of publications, which was I think probably 1 to 8th or 1 to probably 10th with respect to Chinese contributions, and it was 1 to 20th with respect to Americans. There's a little, kind of a narrower gap. So this is something we need to think about, that how we can bridge this gap in future. Because if we were to really make a mark in this area, we need to think about what are the ways can we bring more interdisciplinarity to the work we are doing. Can we also be more solution-oriented? These are some of the things we probably, as an aerosol community in India, we need to think about. So I thought that I will just take this opportunity to share this. Again, I extend a very warm welcome to all of you, especially again, my friends and others who have come from abroad. And I hope you will have a great time over next 3 days within this conference, and also you'll get some time to roam around in the beautiful city of Mumbai. Thank you very much.
Thank you, sir. Our guest of honor for this inaugural function is Dr. D.K. Aswal, Director, Health, Safety and Environment Group. He is currently holding the position of Director, HSEG BARC and Director, National Radiation Emergency Response, DAE. He has gained fame with work as Director, NPL, National Physical Laboratory, and several other important laboratories. In addition to his expertise as a well-known scientist in his own domain of molecular electronics, he has made extraordinary contribution for the projects such as establishment of Indian Standard Time, which has helped in several key projects including Chandrayaan-3. He has been a guiding force for the technical and organizational aspects of this conference. May I request you to address the delegates present here and set the stage for conference. Sir, please.
Respected Professor Grover and other colleagues sitting on the dais, a very good morning to all of you. On behalf of BARC, I again welcome you. And let me congratulate the organizers selecting a date of 12th December, because today the United Nations Conference on Parties, COP28, is ending at Dubai. I have been watching this deliberations at the COP28. It's a big issue. Paris Agreement was that when they analyzed the IPCC report, they found that by 2100, the global temperature will rise by 4.5 degrees Celsius. And therefore, there is a need to cut down the carbon emissions. Of course, there are some efforts, but the efforts are not enough. Interestingly, the COP28 is being held at Dubai, and everybody knows that Dubai is a place for oil and gas. And therefore, there was a conflict of interest to begin with. There was a huge controversies, and obviously, the business will not allow coal and gas energy to come down. There has been a deliberation that we should promote the nuclear energy. And everybody knows that nuclear energy is one of the cleanest energy. The carbon dioxide which is emitted is minimal among all the energy sources. Unfortunately, nuclear energy faces a problem of fear of radiation. And that fear of radiation came from one unscientific paper by Hermann Muller, which predicted that any single photon can create a genetic mutation. So like mutations are good and bad, we know the Darwin theory of evolution. Similarly for aerosols, the general perception is that aerosols are bad. That is not the true. Aerosols are good, For example, in inhalator, when somebody has a problem with lungs and we get this inhalation, because it can penetrate directly in your lungs. But if the material aerosols are dangerous, so definitely it is going to have a problem. So that's why the PM2.5, PM10, and other aerosols in the environment, they are unhealthy. And as a director of NPL, I know one thing. The way we measure PM2.5 is very faulty, and that needs to be addressed. The air quality index, it is very unfortunate that the entire group does not have a uniform air quality index. India, China, we believe up to 500 scale. UK, Singapore, they have a scale of only 10. Many countries, they take 4 or 5 as a toxic element. India takes 8. So this has created a kind of confusion worldwide. And some or other reason, we always have a tendency to project the negative things at the higher scale. If our cities are becoming dirty, our newspaper, everybody says we are becoming dirtiest. In fact, the calibration of PM2.5 in this country does not exist. The standards does not exist. We did some attempt at the NPL to do, and probably that will get approved now. So similarly, when you are measuring the carbon monoxide, carbon dioxide, nitrogen oxide, where do we have the reference gas samples? And the reference gas samples, they are imported, often are compromised, because we do not know how to ensure that the reference material which is imported are correct or not. So India needs to build that measurement capabilities in the country so that we know what is right, what is wrong. So I hope these will be topics which will be deliberated on. Regarding the nuclear energy versus the rest of the energy, tomorrow evening I will give a lecture, and hope you will enjoy that. And with these two questions, how to harmonize the AQI across the globe, it is so sad that even WHO does not have come any definition of AQI. They have said that these are the hazardous parameters, but they have not come up with any kind of AQI definition. So can we have a harmonized AQI definition? In country, can we have the measurement traceability ensured that whatever we are doing? And these are the issues which we can deal in during the conference. With this, I wish you all the best. Thank you very much.
Thank you, sir. To inaugurate this important event, we have here with us the august presence of Padma Shri Dr. R.B. Grover, who has been a pioneer in framing the Indian nuclear energy program, as well as in establishing the academic wing of DAE, namely Homi Bhabha National Institute. Currently, he serves as a member of Atomic Energy Commission and emeritus professor of HBNI, and the chairman of Board of Research in Nuclear Sciences, which is DAE Research Funding Agency. His spectrum of contributions range from technical to education and to policies. I now request Dr. R.B. Grover to kindly address the conference delegates. Sir, please.
Thank you for that kind introduction. Good morning to all of you. I am honored to be here along with all of you for this inaugural function of the national conference organized by the already commented by Dr. Aswal. The 28th conference of parties to UNFCCC is scheduled to conclude today in the United Arab Emirates. While we wait for the outcome, it's clear that to achieve economy-wide net zero, for which announcements were made by many countries 2 years back in Glasgow, the world needs nuclear. There was a side event organized by IAEA at Dubai. The title was Net Zero Needs Nuclear. This is particularly so for a country like India, which has a very high density of population and is not in a position to divert large tracts of land for solar plants or for growing energy crops. Many countries have given a call for tripling nuclear installed capacity by 2050. India has firmed up projects to do so much earlier. And this includes setting a series of pressurized heavy water reactors having a rating of 700 megawatt. And the first of the series has already started commercial operation a few months back. Additional 3 are in advanced stages of construction and commissioning, and 10 more have been approved and at various stages of construction and planning. 4 VVERs, which are being set up at Kudankulam in technical cooperation with the Russian Federation, all of 1,000 megawatt rating, are under construction. And all these projects will be completed within about 1 decade. A prototype fast breeder reactor having a rating of 500 megawatt is at an advanced stage of commissioning. In summary, India will be tripling the installed nuclear capacity within about a decade, much earlier than the pledge by many countries led by USA at COP28. India has to do much more to achieve economy-wide net zero, while the developed world has to replace energy sources with low-carbon energy sources. India has to ensure that in addition to replacing existing energy sources with low carbon sources, more energy is available for growth. As perhaps all of you know, there is a direct correlation between the Human Development Index, HDI, and per capita final energy consumption. India is a part of the G20 group of nations, and many in the G20 have an HDI above 0.9. India has to increase per capita energy availability to improve its HDI. Some estimation have been done by my group in this area, and those estimates tell us that total final energy consumption in India has to triple by 2070 if we want to have HDI of 0.9. About 60% of final energy consumption will be in the form of electricity, and the rest from hydrogen and its derivatives, which will be used in industry and other hard-to-abate sectors. Some hydrogen will be produced by biomass, urban solid waste, etc. But the major share will come from water by electrolysis or thermochemical splitting at high temperature. Essentially, nuclear has to play a very significant role in achieving a net zero by 2070 in case of India. Research professionals present here are aware of the benefits of nuclear energy in terms of low health externalities and the fact that it has been subjected to intense scrutiny by the civil society as well as energy professionals. This intense scrutiny has resulted in the nuclear industry evolving a very robust framework for safety regulation. Right from the inception of the nuclear program, India has emphasized safety at all stages of the nuclear fuel cycle. The safety regulator was established in 1983, and over the years, it has grown to become a highly professional organization. In case of an accident, however unlikely, the behavior of fission products has to be studied to provide inputs for the planning of remedial measures. Towards this end, I would like to make a special mention of the National Aerosol Facility at IIT Kanpur. Dr. Tripathi is here, who has been instrumental in constructing the facility. And this facility has been set up with funding jointly from BRNS, from BARC, and IIT Kanpur. We are looking forward to the results of the experiments conducted in this facility to have a deeper understanding of the open issues and intricacies of aerosol transport and deposition on nuclear structures and equipment. I hope that deliberations at this conference will focus on extending such efforts with renewed intensity. Dr. Balvidra Sapra briefed me about this conference 2-3 days back, and I note at this conference you will be looking at all aspects of aerosol science and technology. This includes material synthesis using the aerosol route, shifting of dimensionalities from micro to nano and now to quantum dots, issues related to air quality, etc., which has been very well covered by Dr. Aswal earlier. Air quality is a very important issue, and we keep getting continuous updates on the air quality index. Air quality issues are so important, and they crowd both print and digital media news space, covering emissions from transport, industry, agricultural practices, and natural sources. During COVID-19, the otherwise harmless aerosols that are emitted by humans during the respiratory process, such as talking, singing, or coughing, gave a nightmare to the whole world. The healthcare management of virus-affected patients became very challenging, and researchers realized that the main culprit was the virus-laden respiratory aerosols. And all of you who are experts in aerosols have to address these issues through your research so that we don't get similar nightmares in the futures. Issues like air quality and the spread of viruses by aerosols are of concern to all researchers, policymakers, and general public. Proceedings of a conference like this have importance for all, and I compliment the organizers for planning this event. It is good to see that sessions cover many topics and that need discussion in the context of air quality considerations. The panel discussion on Mumbai air quality is a welcome step, as in the last few years, we have had days of very poor air quality. I understand that leaders and collaborators of national programs, such as the National Clean Air Program, involved in air quality index monitoring and networking, are active members of this particular professional organization and are participating in this conference. I am hopeful that the results of their campaigns will be discussed, which will help the participants to get directed and motivated to work towards having a good air quality, not only in Mumbai, but all the urban centers in this country. With these words, I compliment the organizations for putting together a good scientific program and wish all participants a fruitful 3 days of deliberations here. Thank you very much.
Thank you, sir. I would now request Dr. S.N. Tripathi to present Dr. R.B. Grover a memento as a token of respect and heartfelt thanks. These tokens symbolize our profound gratitude for your inspiring presence at Iasta 2023. I would like to mention that Mr. Kailash Gharat from Industrial Hygiene Safety Sections, he has taken efforts for this portrait. Now I would request Dr. Pratsinis to stay back and other honorable guests on the dais to please take their seats in the audience, as we will now start with the keynote lecture, which will be delivered by Dr. Sotiris E. Prastinis from Swiss Federal Institute of Technology, ETH Zurich, Switzerland. Dr. Pratsinis is an expert of mass transfer and micro-nanoparticle technology. He has pioneered flame synthesis of nanostructured materials with closely controlled characteristics. He has published more than 400 refereed articles, filed 20+ patents that are licensed to industries, and have contributed to creation of 4 spin-offs. He has received many prestigious awards, including Smoluchowski Award 1995, Humboldt Research Award Germany 2011, Fuchs Material Memorial Award 2018, and the Lifetime Achievement Award in Particle Technology from AICHE. He is AICHE Fellow 2015, and in 2017 he was elected to the inaugural class of fellows of the Combustion Institute. I would now request Dr. Pratsinis to start with his presentation. Sir, please.
Thank you all for coming every morning to listen to my presentation, and in particular I thank the chairman of the conference and Dr. Anand for actually facilitating my visit here. For me, this is a dream to come true, because India, when I was in elementary school, was a mythical country. It was the limit of Alexander the Great's empire that actually had stopped here. And for us, the little children at that time, India grew like an amazing place to ever visit. And during my professional career, I had had a few opportunities to come to India, but always this particular conference is the beginning of December. And this coincides with a major materials conference, MRS Society. And usually I have to be there with my students. But this time, for some magical reason, this conference was a couple of weeks apart, so I managed eventually to come here. So I will start my presentation now with what will be here the actual talk. And I see I have only about 45 minutes to, let's see if we can make this happen. All right. So, what I will try to do in the next 45 minutes, hopefully, is to quote one of the greats of the Western civilization, the St. Paul, to give you a fragrance of knowledge on aerosol synthesis, how we go from aerosol synthesis of materials and even devices to actually a new fundamental understanding of one of the basic properties of aerosol, which is the mean free path of the gas, which defines the transport in the free molecule or the continuum regime, and so many other aerosol dynamics. And also I will give you a glimpse here of our university. As you can see here, the ETH in Zurich, that prides itself. I see, maybe you can. Okay. This was a school that was established in 1855. It has about 20,000 students, about 500 professors, and 10,000 employees. And prides itself that is associated with 32 Nobel Prizes. And some of them you can see here, Einstein, Pauli, or Ernst, or Wuttrich, which actually have been in the faculty or students and associated with our university. And but here we will talk about aerosol particles, and for me, I hope in the next few minutes to show you some of the lab of the field from my students and myself. And first of all, by glancing at the program, I see the focus is on environment, smog. Looking out of the window of my hotel, I see the haze over the city of Bombay. So it's a clear aerosols are part of our daily life in Bombay. And ozone hole, some of the classic problems of the past, and nowadays climate, as it was mentioned, the talks that just finished in Doha. So we're actually addressing some of these issues. Of course, aerosols are important for energy, coal combustion, turbine combustion, catalysts for cars, fuel injection engines, metallic fuels, and flue gas cleaning, some of the classic problems. Also, health. Smoking is a classic problem with aerosols, is the culprit. Allergies, asbestosis, but also can be good aspects of aerosols when actually we're talking about delivering medicine in the aerosol states, and can be a lot of fun, actually. We are sitting on the biggest aerosol particle of all on the Earth. Astrophysics has been my hobby. If you come to Zurich, we have a trail, we call it the Planet Trail, where I usually take my guests, because in Switzerland they have actually put the planetary system, all of these planets, at a distance 1 to 1 billionth and the sizes, so you can actually walk the planetary system overlooking the city of Zurich and its lake. It's a fabulous trail. And of course, stardust. But what would be the emphasis of the talk today will be on what we call the good aerosols, okay? How aerosols can actually help us making better materials and actually improve the life of the mankind. It's not only bad. So carbon black, optical fibers, pigments, photocatalysts, polymers, and sensors, as you will see on my talk, you will see that actually can make a huge contribution. By the way, during my talk, I will talk about some companies. They mentioned in my introduction spin-offs. I can tell you that I have no shares on the spin-offs. I don't have even a seat on the board because I really like the students to really have ownership of their work, and usually that's what helps companies to actually develop without the professor being and overshadowing them. So, where all of this started for materials and aerosols? Well, it started from this continent, in Asia. As you can see here, you see a brave Chinese worker that is actually collecting soot that has been generated by pyrolysis of vegetable oils. And you can see him, he's scraping from the wall the soot without face protection. And this will go to a little vial, and it will make this famous Chinese artwork that all of us were familiar. So Asia is credited for the birth of the manufacturing of aerosols. People, they were using aerosols exposed with the smoke throughout the beginning of the mankind. But here, aerosols, they were made for a specific application. And of course, as a Greek, I should have shown you some vases where actually they have been also using it as well, but the birthplace is here. And by the way, this process was dominant until the end of the 19th century. And actually, if you go to one of the most famous universities on earth, the Harvard University, as you walk into the library, the first thing that you see is the Bible of Gutenberg, and this was actually made with ink that was actually done exactly the same way. So this has been with us for a long time, but of course, the manufacturing of aerosols, the materials, had close connection with the automobiles. When people discovered that actually by adding a little bit of soot into the rubber, suddenly the rubber can last much, much longer. So when people actually can go for thousands of kilometers, and essentially we can, because if the rubber by itself doesn't have soot, then we have to change the tires as quickly as you change the oil. So this, which we don't know how this magic happens, it's the biggest process. And what you see here, you see a discovery that, of course, in the beginning, people, they were burning gas coming from the earth, and it was actually very pricey. And then some colleagues discovered, look, in the oil fields, nowadays, of course, we are taking huge advantage of gas coming from the earth. It is very good. It's one of the cleanest, let's say, sources of fossil fuels. But at that time, it was a huge problem. And people, actually, when they had an oil field, they wanted to burn the gas because it was a big danger for explosion. And what you see here, and you see actually burning the gas, and you see on the red is where the gas is flowing. I don't have a pointer here to spot, but nevertheless, I hope you can see the soot is coming and is collected. Why I don't have a pointer? This was picked it up. This, but I don't see it. I see it on my screen, but I don't see it on the computer, on that screen. You know, what happened, I tried to bring my own pointer, but police came to me when I went through this, and they told me that in Switzerland, having the pointers that I use in the classroom is considered a weapon. So it was confiscated. The police came, and then I took also my pointer. So that's, I have to rely on you. I hope this is not, okay, here it is, excellent. So what you see here, but you cannot show it, it's too bright, this one. Well, we need an old-fashioned stick. I had in ETH, I have a stick for that. But anyway, you are smart and you will know what I'm talking about. So what you see here, this is the gas where it is coming out. So it is burning, and the fraction of the soot is collected at the bottom of this channel. And what happens is that because what we know, thermophoresis, is the soot is collected, and that's how soot was collected. Of course, look what happened now. This is the scale-up. 1940 in the United States. Nowadays, when people talk about oil fields, you see these big cranes coming up and down, you know. At that time, you will see the plume coming out. It will be like 50 miles away. You will see the plumes coming from this gas burning and collecting only a small fraction, 3 to 5% was collected. The 95% will go up in the air, okay? So, of course, this was 1940s, and nowadays, of course, this is done in a better way. This is now how today tires are made, by actually burning half of the oil, and the other half is actually making the soot, which will go into the tires. However, this process is a very, let's say, challenging for the environment, because a lot of CO2 goes out, correct, because you burn a huge amount. It's not inefficient. The yield of this technology is only 50%. For the chemical engineers, this is not an acceptable yield, but nevertheless, that's how it works. However, brilliant aerosol scientists are working now making this technology with plasma, where all the oil, and in the United States, it was the first plant that was built, was making carbon black by plasma, by which no CO2 is actually delivered in the air. So the solutions to our problems is more science, I believe, rather than regulations. But nevertheless, we have to deal with that. Because if you look into the old problems, like the issue with the fertilizers, 100 years ago, the ammonia solution was given. People, they were also worrying about the end of the world at the time because of the lack of fertilizers. However, science gave the solution. Nevertheless, we have to be careful here because carbon black is a big business, 11 million tons per year, carefully made, but at the same time, we are putting out on the air soot, 8 million tons per year. Somehow the different modes in Europe and the United States, mostly by transportation, but in Asia, in South America, in Africa, all of this comes mostly from coal, biomass combustion, and this is a very interesting problem. Why? Because the soot has, it has 1,000 times stronger global warming potential than carbon dioxide per unit mass. That the advantage of the soot is that the lifetime is only about a week to 20 days, depending on the humidity of the environment. So by controlling the soot and minimizing, we can actually gain time to reduce the CO2. So this has a unique opportunity. And actually what we have calculated, and soot is the second after carbon dioxide factor for affecting the global warming. But this is another talk, which is, I don't have the time to talk about it because that's all we have shown, by understanding the characteristics of the soot, because all of these IPCC reports, they assume the soot particles to be perfect spheres. But this, we know very well, it's not. And this makes a big difference in actually in the calculation when of the impact of these components. Nevertheless, let's focus on materials. Now, already carbon black is the biggest aerosol material made today. It's, the value of the business today is about 26 billion per year. And of course, if you ever had a flat tire and you have to fix it and to lift it, remember, 30% of the weight of the tire is carbon black, okay? This is aerosol particles trapped into the rubber. Paints, inks, and batteries. It's a very important component for all of these cars, in all of this electric. And what they want there is a unique structure of carbon black, very fine agglomerates, okay? For tires, we want bigger agglomerates. For inks, so the structure of the materials count a lot. And this is a lot of the area where our students work nowadays. Another major application is titanium dioxide, which is primarily for paints and photocatalysts. And why? Because you can make the snow white of materials. It is the whitest of the whites. And it is in every paint, not only because of the whiteness, but primarily for its opacity to cover the old color on whatever color your paint it is. So it's a major business, and of course has applications in photocatalysis and other electronics and so on. But the biggest, like the carbon black with the tires, is the paints. Another major product is fumed silica, optical fibers. If you have a headache, you need to take a pill. The pill has silicon dioxide. Why? To keep the particles, to keep the pills as pills. Otherwise, they will fall apart. So this is a major product, but it's everywhere. It's a flowing aid and optical fibers. I don't have to tell you much. It was a breakthrough when it was made by aerosol technology. People were making glass, even in this country, by drawing it from the melt. However, when it was made in the gas phase, it was made exceptionally pristine. That's how they could be used for telecommunications. The aerosol technology actually gave that breakthrough. Another application is nickel for batteries. It's another big business, almost $1 billion per year. And the question is, what makes aerosols so attractive for materials? What is the unique? So this is what I would like to say in the next few slides here, because as you make materials in the gas phase, you can take advantage by this rapid heating and cooling. Typically, aerosols like the carbon black are made by high temperature processes. But during the cooling, you can actually capture phases that you cannot find them into the phase diagrams of thermodynamics. Famous for that was the famous martensitic swords, but developed by Arabs in the medieval times and before, actually. And this technology does not involve liquid byproducts. You can easily understand that. And it's easier to collect particles from the gases than from liquids. You can understand the economics and the effort that it requires for that. You can make high purity products, as I just mentioned, with optical fibers, or have a special morphology. There is no technology that you can make these beautiful filamentary structures, but in the gas phase. In the liquid, it's very difficult because upon drying, they tend to collapse, and you don't have them anymore the way you want. And efficiency, as you will, I don't have the time to discuss specific process lines, but it is usually with aerosols, you can make few and fast unit operations. And the typical example is when you have this dry scrubbing from wet scrubbing. You can imagine what happens to remove the sulfur with water and then dispose all of that. And the same reason is you can make the titanium nowadays. There is a big interest to make the gas phase rather than from the liquid phase, just for that reason. And finally, for the educators in the audience, transport, in particular diffusion, if I have time at the end of the talk, you will see why, in gases is better understood and facilitates process design from first principles. It is one of the few technologies, like the same thing with aerospace, that you can go from the computer actually to the manufacturing. It is a unique. Why? Because as you can go back to the fundamentals of diffusion, the so-called Stokes-Einstein equation for liquids has always empirical factors, these steric effects, while the Chapman-Enskog usually gives you the diffusivity within a fraction of a percent. And I think this is where we capitalize in aerosol technology for manufacturing and so on. Having said this, bigger picture, what we do in Zurich, right? We actually focus on aerosol characteristics and how they affect material performance, okay? This is our mantra, this is our message, how the characteristics of aerosols can actually make me better catalyst, better sensors, better medicine, and so on. So it's not enough to make beautiful particles, but what we are looking for is functional particles, okay? This is what I struggle with my students, my colleagues. This is, and you see here, for example, different, in this case, we're using combustion, like from the medieval times or primordial times even, because of this very good understanding we have of this technology. And we have actually two axes of work, fundamentals. And if we have time, I'll give you a favor at the end of my lecture. And applications. And why we do that? First of all, for the academics again, and all of us as a scientist, for the joy of understanding. I mean, this beauty, nobody can take it away from us. And of course, these fundamentals enable process scale up. You will see here that although many technologies have been developed for making materials, being able to understand it so well as in aerosols gives us the capacity to scale up even in the laboratories for kilos per hour. And of course, and also you will see this, well, if you understand something, facilitates and enables product innovation. And what we have been applying our work mostly for catalysis, biomaterials, and sensors. And having said this, what we have learned, because as it was mentioned in my introduction, I have been in the field for some time here, so something we have done all of these years. What we really learned is that, truly speaking, from fundamentals, aerosol synthesis of materials can only be made by multi-scale process design. What you see here is what we teach our engineers. I forgot this. So primarily, we have here a leg as a function of time. And this is what we teach here. Primarily by computational fluid dynamics with computational fluid dynamics and the famous Navier-Stokes equations. This is what we really preach here. And we made, you have developed. Fantastic.
You can move.
Thank you. So this one now as you can see here, is the scale where we teach our students primarily in the continuum regime. However, as you very well know, particles, they are not spheres, as we say, equivalent spheres and equivalent spheres. So for us, it's very important to understand, and for this, we need another scale, the discrete element modeling, as we call it. It's one of the names. And typically, we're using phenomenological expressions for the fundamental phenomena. They say coalescence rate, evaporation rate, and so on. However, if we have, and for that, actually, here we have worked quite a lot with some of our students. This is actually Max Eggersdorfer, who have done quite a lot of work, and I forgot to mention Bert Busser, who is now at IBM. He is responsible for the weather in your iPhone. He got a major award from IBM because he's actually in that part of the company interacting and developing that weather forecast. So if you have problems, maybe he's responsible for it, sometimes with the weather prediction. And then for the next level, actually, is when we really understand the materials reasonably well, like in the case of some of these metals, gold, for example, or titanium dioxide, we can go from first principles to the molecular dynamics and actually see how the particles in detail they form. And some of what we discovered at the end of my talk today with the mean free path of my title, it is actually because of that. This detailed understanding gave us that capacity. Having said this, so let's see some of the fruits of the understanding. And here is the first picture, the scale-up. Well, you see here two colleagues, two of my students, Henry Kamler and Roger Muller, which are both of them now in Novartis. From the bottom one, Roger Muller, who is actually, you see here the scale-up of production of 700 grams of nanostructured silica from a flame. Right now, he's in Novartis. He has about 2,500 people working for him, and he tells me that in his department, the sun never sets. Some of these big companies, they have offices all over the world. So, and here, to give you a magnitude of the size, here you can see my technician, because when you make material by aerosols, making the aerosols is the easy part. The difficult part is collecting them. And what you see here, you see to the right, the technician here, and you see the backhouse filters. And when we were first developing this, our laboratory will be unbelievable, because from little leaks, because of the pressure, they will come out. So you had to really make it carefully, and of course, this was first outside of Zurich. I was able to bring it in Zurich, and of course, the air that comes out from my lab would have to be cleaner than the city of the Zurich air to be able to operate it at ETH. Now, having said this understanding, of course, this did not stay in our own lab. Here I give you a picture from Johnson Matthey. This is, they built this technology with our help in their laboratories in Reading, UK, where actually they are interested more for catalysts, for automotive catalysts. They have their own big mines in South Africa for platinum, and they want actually to develop some of these catalysts in their technology. And let's come to this part of the world. I didn't come here for a long time, but our technology came here. And in fact, we have built this with Dr. Karsten Wegner in Hyderabad at the ARCI in India, here in India, where it is like Advanced Research Center, if I remember well the initials. So they came, they built it up, and actually they made publications. Like you can see here, I'm not even involved, and they actually produce in the order of about 1 kilograms per hour. We started with zinc oxide. I don't know now what they do. Typically, our partners, they develop on their own. But the second major aspect is actually this understanding drives innovation. And here you can see with Professor Lutz Mandler, a member of the German Academy of Engineering, now a member of he's a professor in Bremen, we developed the flame spray pyrolysis process. And what was this? It was actually very similar to the manufacture of carbon blacks. Instead of burning oil, we would burn different cocktails. If you come to my labs, we have actually a little room where we have the entire periodic table of different elements, and the other side of the room has different solvents. So by making the right cocktail, we can make actually all sorts of materials that you like in the by our technology. And of course, the first beneficial of this was catalysis. What you see here, you see Professor Alphonse Baker, one of the giants in the field of catalysis of ETH Zurich. He doesn't have a Nobel Prize yet, but he's one of the great. And he was actually very much interested in aerosol-made particles. Originally, he was working with aerogel. And if you know, this is something that you make in the liquid phase. But this tends to collapse very quickly upon heating. And then it was difficult because in catalysis, people, they use high temperatures. So when he actually exposed to our materials, so you can see here these particles, which looks like, you can see here, this is an alumina particle with the two clusters of platinum. This looks like Mickey Mouse. The platinum particles are the ears of the Mickey Mouse. And but this is very important for chiral catalysis. And this was some of the first projects that we did with Dr. Eto Strobel. And this actually impressed a lot of people, and actually they have published more papers in this field than any other of all of our applications. And in fact, this became so popular that in 2017, the German Science Foundation, the DFG, established a major program for funding PhDs all over Germany by Professor Christoph Schulz at the University of Duisburg-Essen, and the program actually ends this year to understand the fundamentals of this, as they called it, priority technology, because of its capacity to make materials of different size, different characteristics. In the other side of the Atlantic, the Harvard School of Public Health received a grant, 5 million from the National Institute of Health, to develop nanostructured materials by the same technology, because sometimes when you make materials by different technologies, you make different compositions and you cannot make correct comparison, especially for the toxic behavior. And this was actually this effort was led by Professor Phil Demokritou, who is just moved actually now at the Rutgers University, gave him a huge professorship, and of course he's going to build another. You know how it is in the United States. You have to move from place to place to really keep the game going. But nevertheless, this has become part of the so-called genome of toxicity of nanomaterials. This is a very important understanding when coming to that. So having said this, what is the most important aspect of, let's see, what else has been made? In fact, a lot has been made. And to give you a flavor, you can make dental fillers and bone replacement. This is important because sometimes if you put a glue, when actually I first fixed my teeth, they just put a polymer. But the polymer shrinks. And as it shrinks, creates again new cavities. And this is not good. People, they put particles inside. What particles they put in? Originally, they put fumed silica. But fumed silica is transparent to the X-rays. So this is not good. You have to actually put silica that has some signature, but cannot be seen by the eye, but has to be seen by the X-rays. Because if you put a filling, it becomes like the old metal, silver, you remember, which was not so attractive on the mouth. So this was the discovery here, that the patents we made, but of course, did not make a product, because the industry has another game. Here, we were able to make, in a very scalable technology, this single atom catalyst. This is Professor Fujiwara. He's now at Kanazawa University. And I will talk a little bit more about it for devices to make breath sensors. This is our biggest and the latest big success from our laboratory. I will say 2 slides about that a few minutes later. Silica-coated superparamagnetic ion oxide nanoparticles with silver, very important for treatment of cancer, and conductive composites. Here, by putting what you can see here, you can see actually different layers of particles, and these layers can be conductive, can have electricity. Another layer can have magnetic properties. Another layer can have coloristic properties, phosphoric specific. And here is an example when we put this between two electrodes, and you can see that this little LED glows by transmission of electricity because of the capacity to have now this flexible polymer And this is very important for many applications. Some of them deal with actually implantations in the brain and so on, but this is again outside of the talk today. So phosphorus for tumor imaging, you can see here aerosol particles that contain a slightly different dopant, a rare earth, europium. By just increasing a little bit the europium, you can see how you can change the colors here. This is what we call like quantum dots. And finally, for food, this is also very important for food. What you see here, it's actually, we came for, we have our department of, at that time, agriculture, now they call it health, science, and technology. They had the issues because they were working in Southeast Asia to develop for food fortification, first with rice, but here there is an example of fortifying, in this case, chocolate yogurt with iron. And you can see here on the right-hand side, we have here the classic, which is the iron sulfate. But when you put this in the mouth, you can sense the iron. So this has not made it to the market. However, if you make aerosol-made particles, as you can see here, and put iron phosphate, and by the way, to the left, I hope you can see it here. Oh, now it's not moving. Yeah, let's see. Oops. Anyway, this is a non-fortified, regular chocolate yogurt you will buy in the supermarket. This is if you put this iron sulfate, but if you put iron phosphate made in the gas phase, you cannot distinguish the color, you cannot distinguish on the flavor, and that's the target of that technology. Science is beautiful. You can make the Nature, the science papers, but very few of these Nature and science papers actually develop to something useful, okay? And however, I will talk to you that here we have something useful, and actually, yeah, that's what I'm proud to come and talk to you about. This is, one of them is silver nanoparticles. This is with Professor now, George Sotiriou, and what you see here with these vials, you see nanosilver for different concentrations, and this was very important because in 2008, the United States EPA had been petitioned to label nanosilver as pesticide. We had in our laboratory developed some of the first companies to actually make nanosilver. And of course, if you know one of your materials is labeled pesticide, it is the end of it. It is the graveyard. You can no longer play with this, you cannot sell it. And so, although, as I told you at the beginning, I have no part of these companies, they come to my laboratory, my vice president of research, and tell me, look, Professor Pratsinis, we have licensed your technology, and now there is this threat out there, and we want to make sure that ETH is not responsible for it. So what do? We start research with Dr. Sotiriou, and of course, a couple of years later, we find out that EPA has actually somehow blocked that petition and cited a number of papers. One of these papers was this paper also. And the interesting part was actually not only this, that this company, HiQ, that had been actually created from our laboratories in 2020, with this COVID excitement, you can see here the masks and the lovely picture of that virus. And at that time, by the way, Zurich had a huge problem, and we were the only one in Zurich, in the city of Zurich, that we had the FFP2 masks. So as the university closed, the hospital actually took all of our masks for the doctors because we were the only, at that time, as I remember, even a supply of masks was quite an issue. But because we were dealing with nanoparticles, I didn't show you the picture of our labs because we force our students to wear the masks in the lab all the time because I told them, we don't talk to strangers. We try to develop new materials. We don't know what are these materials. Can be very toxic, can be God knows what. 20 years later, we'll find out. So I forced them to wear masks. I saw these pictures, but I didn't show them in this talk here. So what was the fun part? That this was the first ever ETH spin-off to make it to the London Stock Exchange in December of 2020 because of that. In the beginning, they had actually developed the focus in high fashion industry with toxic, actually antibacterial clothes, but this valued 127 million, and my students told me that their revenue in 2021 was 51 million. But that's not the only one. Another company has to do with biomagnetic ferrofluids. This is cobalt nanoparticles. by the company's Turbo Bits, and this is a creation of my student, now Professor at ETH, Wendell Stark. If you work experimentally and in your laboratory you have an Aldrich catalog, this product comes actually from our laboratories. And actually, maybe you cannot see here, the price for 500 milligrams is almost $100, which means, of course, that if you do the calculation for 1 gram, this is $200. So we're talking 200,000 per kilo. Imagine the gold sold today in New York, $65,000 a kilo. So the particles that you make can be more expensive than gold. Of course, when the company told me they sold the kilo, they sold it for about 50,000. They didn't sell for the market price that you see here from Aldrich. But nevertheless, it is in your laboratories, that catalog and that product. These particles in specific are very important for our professor Inge Hermann, who has actually started this company with Professor Stark, Hemotune. She's now professor at the University of Zurich, which is actually, because of the magnetic capacity of these particles, you can use them to clean blood for very important illnesses, sepsis and so-called blood poisoning, okay? And this is an important illness, and the colleagues of mine actually passed away because of that, as I know very well. It's not trivial. There is another company, Avantama, who is actually, they are the most ambitious of all. If you go to their webpage, they have the entire periodic table, and they ask you, choose the material, choose the composition, and tell us what you want, and then we will send you the quote. And if you like it, then we will send you this, you can see here, these vials, where actually your particles come. It's actually quite pricey, but nevertheless, they can show you the capacity you can make with the materials. Now, the latest of all of those is these gas sensors. And these are very important to monitor because a lot of people work very hard on the gym, but they don't see a difference, okay? And what we actually found by monitoring the breath acetone, what we learned, we managed that actually the real fat burning takes place after the gym, okay? But most of the times people after the gym, they will go for pizza or for beer, and of course they stop. This is the scientific results now. Why? By monitoring the breath, as you can see here, the student working very hard, and then we were able to monitor all of that. But the latest success story is this company now, Alivion again, and what you see here, this company managed to develop a sensor to distinguish methanol from ethanol. Especially in this part of the world, there are a lot of incidents of alcohol poisoning because people, they bootleg alcohol and they don't actually separate the methanol that comes first from the ethanol, and this actually results poisoning, blinding, and so on. And by a clever combination of aerosols made and by direct deposition onto these electrodes and the chromatographic column, and that's what you see here. I show you here this in detail because later you will see the actual device and you don't see anything. So the sensor is right here on the white little box. And here, this white little column is where the separation takes place. And this is exactly what we do with chromatography, having, you know, the different compounds coming at the different times. By comparing the time of the methanol from the ethanol sensing, bang, you have very accurate. And what is the beauty of it? With the blue box here, you can see actually the actual ethanol content. So if you get a drink, you say Johnny Walker, 40% ethanol, you have to see it. If it has more or less vented and it's less, you can say to the barman, wait a minute, this is 35, white is. So, or if it has methanol with the here with the green, you can actually see the permissible level. If it has a lot of ethanol, having a little bit of methanol is not bad because these two compete for the sites in the brain. But this is the story now. And now let me show you the actual product. This is what I show you. This is what is inside of this little, and you can see how it's held here in, with a student at the time. Now he's Professor Guntner. He's actually Professor at ETH Zurich also, and monitoring the distillation process because our first customers were distillers. They wanted actually to make sure that the cut of ethanol from methanol is actually precise because right now it was done by masters, by the smell, by the feeling, if you like. Right now you can do it scientifically, and you know exactly where to cut it. And the second major client they have is the taxation agencies, because when they import alcohol, they want to know exactly how much alcohol, and don't do it quickly. Because if you go use chromatographic columns, these big DCs are quite expensive and so on. So this company was created September of 2022, and now they gave me this slide that they have customers, and you can see all over the world, within a year. All right, 23 countries actually have picked up that gadget. Primarily has to do with federal administration, people who actually look into it. Not yet. Ideally, the dream was to have something for me, like the tourist. I come here in a place, so I need to check the drinks that I get. But of course, these people pay much more, the distillers and so on, than the people to sell it. But this will come to us. I hope up to this point I gave you a flavor. What is the beauty of aerosols and materials? What drives us, the excitement that is actually making all of these things. However, when we did all of this, I saw that my time is already run up, eh? Wow, sorry guys. Well, let me tell you one thing then quick. What I have teaching you from my papers that you mentioned, I have to correct all of that. Because the mean free path, what did we assume? That the gas molecules, they come and they collide like billiard balls. This was what people like Maxwell believed in the 19th century. And of course, because we are mammals, all of us, we copy the previous authors, and we don't dare to question the authority of these major scientists. So we end up, propagating that, if I can call misunderstanding. Because nowadays we know that particles, even more particles, they have a field around Lennard-Jones. What happened? The gas do not have. They do. And this is what is the whole story. And in fact, by two brilliant people, Dr. Dimitris Alikis and Professor Vlasis Mavrantzas, we said, wait a minute, let's take a look here. And we looked into this and said, look, these are diatomic, like this is oxygen and nitrogen. Let's take air, what we have in the room. And let's do the calculations. And what we wanted to really learn is, can we determine the true number of collisions? Because we know this diatomic structure. And most importantly, the field around them, they should make a difference, something. And of course, we worked very hard on this. And I will go quickly on the next slide. You know this Lennard-Jones potentials with the attractive and the repulsive part. I don't have to elaborate the so-called spring model between them. And then you have these two special cases. If we have this calculation done right, let's assume again, like Maxwell, perfect spheres, but with a force field, or perfect spheres and forget about the fields. Let's see a hard sphere that's colliding like billiard balls. Or make another case, perfect spheres with a force field. The real thing is the atomic and the force field, correct? So that was the whole motivation here. And let's say collisions, how they look like. Of course, if we take the hard sphere model, it is behaving exactly as Maxwell and whatever we have in the textbooks like that. Bang, bang, okay? No questions asked. Now, if we go to the next model, which is the Lennard-Jones, perfect spheres are with a force field. Now you have to be careful. They come close, they do a little bit, and a soft touch and go, correct? That, I hope you saw that. And there is a little kink in the contact over there. And if we do the real thing, of course, it is more obvious what is going to happen here because of the rotation of because here you have they are not perfect spheres, so you have to account for the rotation of the diatomic structures, and that's what you have here. So when you have this, then you can have the first thing is multi-body collisions. In the interest of time, I will skip those. Trust me, we have 3-body and then 4-body. And even if you go to lower temperatures, you can have even a 6-body. That's something that I don't even have it on the lecture. But let me go one step further. The interesting part, the fact that actually made me to come here and talk to you today is this part, because when I discovered this, I did not believe it. Because the students, they come and tell you, must be wrong, okay? But wait a minute. What happens here, if in some cases, depending how the particles come, look how they collide, bang, 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 and later on they will go away, all right? And this is in the ideal case of Lennard-Jones, perfect spheres, but with a force field. Now let's see what happens, the real thing, okay? Now if we allow them to move, we have kept stationary the green, and then you can see comes, they will come back again, they will bang, and they will come back again, trust me, they will bang, and then they will go away. This is what we call spurious collisions. And of course, this is something that we have never seen before. And actually, my advisor, Senator Freelander, had told me, look, if you have something new, it's not really new. Someone must have seen something somewhere, somehow before. And this is somehow kept in the back of my mind. And of course, with this result, I was sitting on them checking cases, different force fields. You know, for those of you that are molecular dynamics, you know there are all sorts of force fields out there. And we're getting the same results all the time. And this is exactly the two things that I showed you, correct? But when we discovered this, if in this book by Hirschfelder, Curtis, and Baird, that actually they have said, look, because of the force field, and these people, Baird, for the chemical engineers, has written the Bible of chemical engineering, the transport phenomena, Baird, Stewart, and Lightfoot, for those of you in the audience. And they have actually talked that maybe molecules can go like that. Of course, they will have these banks, as you see on the B here. But they said also, under certain conditions, you will have this, and they call them orbiting collisions. And that's exactly what we have here ourselves. Of course, these people, they didn't have these details of the dandelion that comes as you go around. And eventually, of course, this tells us, wait a minute, you have something real. And this moved us further to calculate number of collisions by the kinetic theory and the hard sphere. And we see here perfect agreement, the number of collisions, which gives us another good validation. I forgot to mention that we have validated all of those by matching diffusivities, air densities, and air viscosities, because otherwise you can carry yourself insane. And if we have, of course, the Lennard-Jones model, we have far more collisions or fully atomistic. But of course, the collisions that I just mentioned to you, these ones that are orbiting these spurious, we filter them out. We don't count them, okay? These are collisions that they don't matter. So if we now calculate the collisions, we develop this probability diagram as a function of the free path. And you can see here, as you observe the statistics now, essentially you converge on this. You go from the green at a half a nanosecond, at 1 nanosecond the blue, 6 nanoseconds the red, and you can see they're converging on that. From this distribution now, we can get the value that goes into the textbooks, okay? This is the mean free path. And when actually we do that, we actually see that what we have on the textbooks is this 67.6 nanometers for room temperature, but if we do the hard sphere model is 70.6 plus minus 2. You can see here, it is the mean free path as a function of the observation time. And what you want to see, you see the statistics, and you see that they really, oh, you even have this? Oh, this is good. Now, you can see here that they really reach this asymptotic value, and that's what you see here. If I have this Lennard-Jones model, goes to about 42.3, and if I go to the fully atomistic, we see now that the mean free path is not the 67, but now 38.5. And this is 43% less than the kinetic theory. Of course, you may tell me, so what? I'll tell you the so what. First of all, immediately, is you can use the continuum, the Navier-Stokes equations, to even smaller particles. You don't have to stop at the 500 that you had before. Second is, it's very important for this subcritical cluster nucleation dynamics. This is, the mean free path now affects a lot of their mobility, and diffusivity of nanoparticles is a long discussion, first with Professor Tamet in Estonia, then with Juan Damora, Zhang, and I'm afraid that I don't have time to go through my entire talk. I see I'm already coming to the absolute limit, but nanoparticle coagulation, and if I had time, I will actually talk to you about diffusivity, because here, diffusivity of particles, of very small particles between less than 5 nanometers, is an order of magnitude smaller than that of the Epstein equation in the textbook. So what we have now on this nanoscale, we actually have to rethink the aerosol dynamics. We have to think how all of this come into picture, and why I was driven into it. Because if I want to make particles less than 5 nanometers, the self-preserving theory or the Mandelbrot fractal dynamics, they don't allow me to reach these asymptotic values that we use, the 1.45 in, as you have seen in my old papers, of the geometric standard deviation, or the 1.8 of the DF. That's why I was motivated to get into this 1 or 2 nanometers and end up having to that. Let me stop here because I have to respect the organizers. They made all this effort to make this beautiful conference. And the great news is that you can read all of that on this paper that was published last month. The other stuff that I want to show you is what I have not published, but this is even the exciting part. But maybe let me stop here, maybe quickly go to my conclusions, and because I have to say some conclusions, otherwise I will let you walk out without getting the flavor here. And this is maybe to get the message. I had that you see a lot, but you can talk. I will be here all 3 days, so we can really talk offline, show you the slides, whoever really cares about it. So I hope I gave you the flavor that a wealth of materials and devices can be made scalable by aerosol technology. What excites us right now is that we are able to relax the assumption of kinetic theory. We don't have perfect spheres. We don't have elastic collisions. And because of that, you can actually distinguish genuine from these spurious collisions. We can even collision densities and mean free path from the hard sphere model match exactly the kinetic theory. And by accounting for the shape and the force field of the gas molecules, we can actually have a much smaller mean free path of what we have in the textbooks. And what I did not show you is that a new expression for the diffusivity is actually going to develop and submit in the following year a new Cunningham correction that actually connects the entire thing from the molecule to all the way to the continuum. Thank you very much for your attention, and I'll be happy to answer any questions you may have.
Thank you for such an interactive, interesting, and enlightening talk, sir. Your presentation has undoubtedly enriched our understanding towards nanostructure and materials synthesis and such wide range of applications. Towards the subjects, I think it would enhance our understanding. We would like to get a few questions from the audience. 1 or 2 maybe.
Thank you, Professor Pratsinis, for a very inspiring talk. Actually, when we try to attract young talent from engineering disciplines to aerosol science, one block is always the fact that it speaks more of negativity. It is the work of your type which we tell them that there are a lot of positive aspects of aerosols, and you have really illustrated that point. I have a question, more of very excited about hearing your last slides, the kind of topic which some of us have worked. So you were orbiting, discovery of orbiting motion. If I go back to work of, when they were doing ion capture modeling, Kiefer, Nolan, and Rich, the old trajectory model people, I distinctly remember the statement that if you have anything other than the universal square law, especially the image forces, their final capture is via a trajectory orbiting motion. Yes, because you have closed orbits only for universal square law. For any other law, it has to make collisions and then capture. This is a classic result, not molecular dynamics. That is one part. And I'm quite interested in that now that the Knudsen numbers are going to change and you have new results coming out, more or less the continuum model might work for far lower sizes than what now assume. Is that the kind of conclusion that you're saying, that we can extend the continuum models closer to nanoparticles than what we generally do, so that the so-called unsolved problem of transition regime can be sort of avoided?
Actually, yes. This is what we have now. We have actually a capacity to bridge the gap, as you will see here. And we see it's a matter of actually computational. As we grow up, actually, and let me go back to slides that I skipped. Maybe this will give you, okay, you can see here, this is the final story. This is this is, thank you. As you can see now, this is what I will hopefully publish sometime next year. where will be a new Stokes-Cunningham expression, and you can see this is the latest one. This is by paper by Jung, Mulholland, and Pui, and you see here, and we only changing this factor. So what we really have to account is actually, for this small size, not only the particle diameter, but the molecule diameter. Because now, when you are to the nanoscale, 1 nanometer particle, when the gas molecules are 0.3 nanometer, this is relevant. So this is the new thing, and this is what helps us. And if I go one slide back, you will see here, for example, these are the molecular, this is the Stokes-Cunningham with the Epstein expression that matches up there. And you can see these are our calculations. And you see, they are almost an order of magnitude below. The diffusivity is much smaller. And now by these computational tools, and I believe in India, I had brilliant Indian students that beautiful mathematics. I believe this will help us rewrite that part of aerosol dynamics. I think this, if you really look, even the kinetic theory coagulation is not on a firm grounds. This actually, if you read carefully, the continuum is reasonably well done, but the free molecular regime is not so sharp. So I believe in the next few years, we will make a new based on these tools. I don't know if I answered your question, but this is where we are heading. Thank you. Other questions? A young lady over there.
Yeah, I think we can take up the questions during the tea, please. Now I would request.
Let one student, maybe junior scientist,
Yeah, good morning, sir. Sir, I have a doubt for like a basic doubt I'm having. Sir, am I audible? Yes, sir. Yes, sir. So related to the aerosol characteristics, I am having doubt, specifically towards the aerosol density. Like we are having several methods to calculate the aerosol density. For example, the chemical composition. By using chemical composition, we can take out aerosol density, or the mass by using the mass concentration and number concentration. So these methodologies are neglecting the, like you have talked about the hard spheres and the soft spheres and the trajectories, and about the supersaturated contents. Like they're neglecting the meteorological impacts. So how can we calculate the aerosol density by considering these things, hard spheres or soft spheres, so that we can have the accurate aerosol density instead of neglecting some parts like.
Very good question. The question is, what really means this with what we do until now? I mean, probably this is the question that you ask. And as you can see on this graph, if we go here, the scale is a particle diameter, this is nanometers, and this is the classic Stokes-Cunningham expression with a black line. You see, from the 10 nanometers and up, we don't need to worry. But below 10 nanometers, this is where correction. So if you like to make particles, as I do, 1 or 2 nanometers, the current expressions are not sufficient. I need more accurate ones.
Yes, sir.
But if you are working in the, let's say, measuring particles, this is going to be important for the people who develop instruments, who develop ways to characterize nanoparticles. The new mean free path has to be entered into these models, because most of the time they convert a light signal or an electrical signal to particle characteristics. That transmission requires the correction, especially below the 10 nanometers. Did I answer your question?
Sir, for smaller particles, for the very small particles. Yeah, sorry.
Okay, I will be here all 3 days, so make a mistake. We cannot miss me. Maybe I can see now, right? I have to wait.
Now may I request Dr. B.K. Sapra to present Dr. Pratsinis a memento as a token of respect and gratitude.
Thank you.
Thank you, sir. Thank you, ma'am. Yes. As you are all aware, the new managing committee of Iasta has taken over after January 2023 Iasta elections for the next 3 years. Various activities have been initiated and many more are planned. I would request Dr. Manish Joshi, Secretary Iasta, to present a glimpse of these activities. Dr. Manish Joshi.
Good morning and a warm welcome to Iasta National Conference 2023. We are already running short of time, so I will directly go to some announcements. So our current team is being led by Dr. S. Tripathi, and the activities which I am going to announce or present is the collaboration of all of our members, which are spread across different institutions of the countries. We are already conducting a very successful monthly online lecture series, which is being attended by many enthusiasts across the country, and which is we are taking inputs or we are taking experts from different countries of world. Then we are actively participating in different events of national importance. Like we participated in, we had a session of ISI in India Clean Air Summit. Similarly, different theme meetings are being organized where ISTA keeps on participating. We are going to now start a new series which is called as a Learning with Iasta series, where we will be aiming to educate students, college, university students, as well as general public, whom we should be sensitized about the air quality issues. Here we will be involving all Iasta members. So this program will be initiated very soon. Coming to some events now which ISTA is planning in year 2024 and 2025, we have an extraordinary response to this conference. So we are planning to have some more events in future. Like in 2024, we plan to have a summer and winter school, as well as some workshop and a theme meeting. And different members can be to conduct these events at their institutes as well. And coming to this next year ISTA conference, this is already now taken shape. We will be having this conference conducted at Doon University, Dehradun. And ISTA is also bidding for Asian Aerosol Conference and International Aerosol Conference to be conducted in India. So that's all what I want to say. Time is short, so let's go to the next event. Thank you very much.
Thank you, Dr. Manish Joshi. Now I would request Dr. S. Anand, Treasurer ISTA, to deliver a formal vote of thanks.
Thank you. Good morning. On behalf of Indian Aerosol Science and Technology Association, I extend our deepest gratitude to our esteemed Chief Guest, Padma Shri R.B. Grover, Member Atomic Energy Commission. Thank you for accepting our invitation and sharing your wisdom and expertise with us. A special note of appreciation goes to our guest of honor, Dr. D.K. Aswal, Director, Health Safety and Environment Group. His support and encouragement have been invaluable. We express our sincere thanks to our keynote speaker, Professor Ratnesis from Particle Technology Laboratory of ETH Zurich. Your illuminating address set us the tone for this conference. Thank you, sir. And our gratitude extends to all the plenary and invited speakers, platform and poster presenters, and participants of this conference. A special note of thanks goes to our sponsors and supporters, specifically a big list, industrial sponsors, Alpha Tech, Tiscon, TSI, Mars, MNG, Vasti, Metrom, MTP and AirSed. And also there are a few government sponsors. We thank everyone for contributing and supporting this conference. On behalf of ISTA, again, I would like to acknowledge the hard work and dedication of this national, local organizing committee, technical program committee, also the volunteers and support staff from DRC, security, and all the accommodation providers like TIS, Homiba Center for Science Education. Please accept my apologies if I have missed or forgot to mention anyone. Thank you very much. Thank you.
Thank you, Dr. Anand. With this, we come to the end of our inaugural program, and I request all the participants to stand in the honor of our national anthem. Thank you, everyone. Now we would disperse for high tea, which is arranged at al fresco in S floor. I would request all of you to assemble back here within 30 minutes. Thank you for being part of this momentous occasion. We can take stairs from the front door, and if you want to take lift, you can go from the back door. Thank you.
clearly, that's the tricky part in the secondary particles. You also want to know actually where these secondary particles are coming from, because they're originally gases and are forming these secondary particles. You don't understand that all to actually figure out why is this person suffering from actually inhaling these. I'll start off with this figure here. I showed this actually in Ahmedabad. The one in Ahmedabad. And this was a paper we published in Nature about, it's just a huge haze event in China. And this most cited source portion paper in the world to really show what are the main sources driving the particles. The one main message was really that this secondary species, even in wintertime, you would usually think in winter there's not so much secondary particles being formed, but actually also in wintertime you have a lot of these secondary particles. Well, we can think, we found actually out quite a lot of what are we doing since then? We published this in 2014. So what was driving the future? And I think there are three main questions we wanted to address maybe in the next 10 years or so, and I'm going to show some of the results here in regarding this respect. So what were the shortcomings that we had during that time? One thing was, it took really a long time. We took these filters, took them back to the lab, have to do a lot of analysis, then the source apportionment, and so on. So it takes at least months or a year or even more years to figure out what are the sources and then really come up with a conclusion and what you can do about these sources. So one idea was, we want something, source apportionment right away. Like in minutes after the measurements, we want to know actually what the concentrations are. The second thing is, this secondary, I mentioned it already before in introduction. We want to know, what is this exactly? What are the sources of these secondary ones? When we talk to people in China, also sometimes in India, it's actually one of the main questions, because kind of the primary sources one kind of knows, one maybe doesn't know exactly how much each component is contributing, but especially the secondary ones are actually quite unknown and unclear actually where they're coming from. And in China, that is one of the major things still that it remains to be done, and they really don't know actually what to be doing. So we should find out better where these secondary ones are coming from. And the third one, I think, is, what is controlling really the health risk? Because, a lot of these studies that, are actually using just PM2.5. But we can imagine all these different particles with different chemical composition surely have different impacts on health. So we actually want to know how these different sources are related to health. Okay, so I'll go through a little bit these topics here and show examples of our research in Europe, in China, and in India. Okay, just as an introduction, a little bit on the health side, what I've been looking at a lot, and there's a lot of studies now, especially in Europe, that are actually betting a lot actually on using oxidative potential as a proxy, or as an indicator really for the most adverse health effects. So I think what is happening, these particles that we inhale, they produce this reactive oxygen species, and you can think about it as this, that in our lung fluid or so, we have antioxidants that protects us actually from these oxidizing species. But if there are too many of these ROS species, then our lung has a problem. Then we can have inflammation, and at some point even then cardiovascular diseases or so. This is more the toxic path when we look at it. And if you think about epidemiology, one tries to directly go from the diseases and relate them, for example, to PM2.5. So PM2.5 with different types of mortality, that's how we try to link things. But, if you think now, these reactive oxygen species that are very likely, responsible for these cardiovascular diseases, we can think about, where are these coming from? And what we're thinking is, at the end, maybe we will have new plots here, maybe reactive oxygen species, or maybe we have also different types of sources that we have even better constrained curves here on what kind of health impacts are actually being driven by different components of the particles. So what we do now often is, well, we do the measurements of OP, we do source apportionment by using other equipment, and we actually then infer actually the sources of these reactive oxygen species to actually figure out, I mean, which sources are the key components actually that drive our health impacts. Well, there are different of these oxidative potential or reactive oxygen species measurements, and just a couple here, I will not go into detail, but this DTT, this is, I think, probably the one that is mostly used, and it also has been shown in a review article that this has been shown to have most positive association actually with some of these diseases. So one thinks, at the moment at least, this probably to be the best proxy that we have when using acellular assays to estimate these health effects. So I'll focus a little bit on DTT in this presentation. Well, we were able to publish a paper in Nature a few years back now, where we actually did all this. I don't have time to go in all the detail. So we figured out the sources, we measured oxidative potential, we put the results in a model, and then actually, checked, which actually components of the particles are driving mostly the mass, and which components are now driving this oxidative potential. Basically the toxicity of the particles. And you can see the main drivers of particle mass in Europe is actually, in the north, it's mostly secondary inorganic aerosols like ammonium nitrate, ammonium sulfate. In the south, because of the closeness of the desert here, it's actually more the it's more the crustal materials that are dominate as is the main component of the mass. But if you look at what is now toxic, actually these main components are not there. They're not toxic. You can inhale ammonium nitrate, ammonium sulfate. This is a salt that is not, it will not really affect your body. But if you have vehicular wear with transition elements inside, or you have secondary organic aerosols that actually contain some of these reactive oxygen species and so on, then actually, you will have problems. And you can see in urban areas, it's actually mostly vehicular wear, and in general, it's actually this secondary organic aerosols that comes from anthropogenic emissions that is actually dominating actually the health impact. You also have a little bit of biogenic SOA in the north, where mostly it's coming from actually natural emissions. So this is a starting point from Europe, and we did now some studies, and we're still working on them actually in China and in India. And so what we did in China, we actually measured at 6 different sites. We measured with our instrumentation and oxidative potential. We measured the concentration and that toxicity. And also in India, originally we measured at 4 sites around Delhi and in Kanpur, and recently also in addition measurements in Lucknow and Pune. We did some of these measurements. And if I look now just at oxidative potential and PM2.5, these are now results from Europe. And you can see here now different sites that we have been measuring in India and in China during some campaigns that usually lasted maybe around half a year or something like this. So you can see, well, in general, actually, the data lies pretty much on the lines. You could say, well, maybe ambient PM2.5 is actually not such a bad proxy actually for the toxicity. What you see to some degree is actually the station in India. That the particles seem to be a bit more proxy for the same particulate mass than what we see in China. But overall, it's actually quite similar. But when we look at this a little bit more detail, first going actually to China. So these are now the cities in China, and you can see on average, this really good correlation. But if you look at actually, every day's measurements, you can see that actually for the same ambient PM2.5 concentration, there is actually quite a wide range in oxidative potential. So for example, here, if you take this 100 micrograms per cubic meter, you can see this concentration here of oxidative potential that's actually varying by 1 order of magnitude. And there is actually, that's caused by this chemical composition or the sources. So for example, if you have more dust particles or so, this is for example, here in Beijing and Langfang, some dust storm events, I mean, you're kind of, at the lower end, actually, of this correlation. So you have kind of a lower oxidative potential per PM mass, and so on. So that's the key, and that this variability is actually being used to actually then figure out, I mean, which sources are really contributing that much. Well, if you look in India now at the different sites, I think what is really interesting, and this is quite fresh slides that were put together by people in my group, I mean, putting really now all our data together, is actually, when we see here, the Indian data is actually a bit narrower. So it seems like, I mean, the variability actually between day to day is actually a bit lower. And we'll come back to that. I will show that actually mostly, especially the organic aerosols, is actually driving a lot actually of this variability. And at least during the campaigns, I mean, that we had, I mean, we didn't have, for example, that high dust contributions as we had in the campaigns where we did measurements in China. So things I mean, are a little bit more aligned than actually compared to China. Well, I said we want to also know better, with these secondary organic aerosols, where they're coming from. And there has been some developments that we have also led in the recent years. I mean, one went actually from this aerosol mass spectrometer that gives you quite some good insights in the organic aerosol fractions. Especially, you can separate very well primary from secondary organic aerosols. But we're still lacking a lot of information because of this hard ionization using electron impact. So we developed an inlet in front of a mass spectrometer. I mean, the different types of mass spectrometers you can be using. And using extractive electrospray ionization, you can measure the molecules in their intact form, and that provides much more information. And you can use actually these two instruments in two ways. You can actually do online measurements. So Varun Kumar, who is also here, he actually measured actually with the online method of these two instruments, actually online in Delhi, actually, the concentrations and the sources of organic aerosols. But you also can actually take these, I mean, high-end online instrumentation and still use offline filters and actually get the same information here. Just to give you a little bit of a flavor of what you can get. So this is, for example, anthropogenic secondary organic aerosols from toluene. This is typically emitted by cars or biomass burning or so. And you can see that for the aerosol mass spectrometer, the spectra that we get actually not so much different than actually from biogenic secondary organic aerosols, which is a totally different molecule. But with this novel mass spectrometer now, extractive electrospray, you really get the individual ions, and they still reflect a lot of information actually of the original molecule. So you have aromatic compounds, I mean highly oxygenated ones, but still with the original aromatic structure, and here more in more alkane-like structure here. You can really start in using these fingerprints here, I mean, to start distinguishing actually also, I mean, the sources actually of secondary organic aerosols. But you can see it's complex, I mean, there are actually thousands of molecules being produced actually just, from a single compound. So it's kind of tough. So Deepika has been looking at now offline with the EASY at these at the organic aerosols in Delhi and in Kanpur, and I will show just some flavor actually of what we can see here for some of the PMF components actually that we got from this study. So we have biomass burning. And actually, biomass burning, I mean, if you look at the mass spectra that we get, it's actually quite classic. We get mostly anhydrous sugars, levoglucosan, that has been often used as tracer for biomass burning. We see that also, I mean, that molecule actually in our mass spectrometer. So it's strongly driven biomass, I mean, primary biomass burning actually by these levoglucosan and other anhydrous sugars peaks. Then there's some, for example, this peak, I mean, we could never detect with the aerosol mass spectrometry in this detail. So we see some primary organic aerosols, especially in the cold season, that are very high, that contains a lot of CHN2s. So it's a primary component that actually contains 2 nitrogens, and is known, for example, that cow dung burning actually is contributing a lot to such compounds. So we have some primary organic aerosols that are related to biomass burning, and especially cow dung in India could be a major contributor here. Then we have some secondary components here. You see also much more detail here. So we have, for example, this also in cold season a factor that contains a lot of nitroaromatics and nitrofurans that you can see here, again nitrogen-containing peaks, but in this case also containing oxygens, which provides you additional information actually on the organics. Or here one secondary organic aerosol is more from urban sources, and you can see this has, the blue one here is more nitrogen-containing species, and this is just carbon-oxygen family, and you can see this has a little bit less nitrogen. And if you look in the details of all these products that we see, it's actually mostly oxidation products from single aromatics that are mostly coming from gasoline emissions or from traffic emissions. Also long-chain alkanes, then rather coming from diesel emissions, actually. And then also some cooking that, you actually have some long-chain unsaturated carbons that you see here in the factor. When we combine this data with this oxidative potential, now we can actually estimate, also now for India, actually for these sites, which are the driving factors actually for the toxicity that we see. So you can see inorganics are quite important, ammonium nitrate and ammonium sulfate as well, but it's only contributing to PMS, and it doesn't contribute to any of these oxidative potential markers. So let's focus here, because of time, only on this DTT that I mentioned, maybe most important. So you can see here 3 factors contributing most. One is actually primary traffic. So this is a bit different than what we have seen actually in Europe. We also have a contribution from traffic that is significant, but it's quite much lower. So it could be that the fleet that we have in India still with older cars and so on, or maybe not as well maintained as in other areas, that the traffic emissions still contribute a lot to the toxicity. And then we have these secondary organic aerosols that actually contributing here a lot to the secondary organics. But in general, we can actually conclude here, it's actually, it's really those components where you have a lot of very inefficient burning conditions. This produces primary and then also finally secondary organic aerosols that also are very toxic. So anything that is non-efficient burning is really something we need to avoid. So for example, trash burning in India, I'm sure it's one of the worst components that is also, also within some of these components that we have here. I'll move a little bit to China, just also give you an impression, what we can really do. So we have this oxidative potential now for these different cities as a function of time. And you can see that we now really can, get as a function of time actually the type of sources that contribute to the toxicity by combining source apportionment results. And you can see here for China, we actually have much more different factors actually contributing, but you can see we can actually explain at all these different sites a lot of these contributions. And I think I want to, for discussion, move to this slide here. So this is again the PMS contributions, and this is now the contributions of the PM components to the toxicity. And you can see it's again quite different as in Europe. The secondary inorganics is in China. The blue ones here, they are missing here. So they don't contribute actually to the toxicity, but they're important in the mass. And you can see at some sites here, this is the dust and the urban dust. It's especially in springtime in Beijing, for example, really huge contributions here. But in Beijing, you can see, well, it's actually not that high for toxicity. We start to see now some impact in comparison to Europe of the dust, but the impact is much, much weaker. So in Beijing, We still have, as in Europe, actually traffic non-exhausts, especially breakwear particles that are important. And for the other sites, it's kind of the secondary organic aerosols that I just talked about in India, and also primary biomass burning, or solid fuel combustion in general here, that actually are driving actually the toxicity. I just want to also say some words, because we didn't get the opportunity to really talk about the real-time source apportionment approaches. So what we have also been developing for China is use this combination of instruments to actually get, information about the sources in minutes. We don't want to wait too long. Okay, I hardly have any time. So we can use these instruments, and we could show that using combination of source apportionment of ACSM, exact, and ethylometer, we can actually get this information, every half an hour, because that's about the time resolution of the ACSM or the exact here. So only minutes after we had the last half hour, we can actually provide you, with actually the composition and the sources. So we've done that for all the 6 cities in China. So these are some average contributions here. And we tested it at least for elements also in Lucknow and Pune for India. So you can see here going actually from December to April. For example, in Lucknow, we go from a lot of chloride and sulfates in wintertime, then to more dust in summertime as a function of time. And when you actually compare now our most sophisticated source apportionment analysis that we can do with the real time, you can see this data lies, an incredibly good correlation. That means we are really able with this real-time source apportionment to, within actually no time, without any user interaction, actually to predict what the sources are. So I come to my conclusions. Source apportionment is now possible within minutes after measurements. Some of the methods we used in China, we want to use in India in the future. There's new instrumentation using molecular information that provides us much more insights in the secondary organic aerosols. Links to sources of health is really important. I think it's important to pursue further. You saw some of the results here I just discussed in China and in India, a bit different. For India especially, inefficient burning, that's I think really it's the key for, to reduce that for the toxicity of PM. We're really keen on keeping and also expanding collaborations in India on source apportionment and health effects. I think it's a very complex topic, and we need to be collaborating. And I think more research will be presented here later on, and we also have a source apportionment workshop in Mumbai from Friday to Saturday. Thanks a lot.
So thank you so much, Dr. Privat, for such a wonderful, informative talk. So we can have a few quick pointed questions. In the interest of time, we will not be, okay.
Thanks for the wonderful talk, Professor. I have a simple question you showed that a mass spectrum of novel AMS and a chart of AMS. How you are able to distinguish between the aliphatic and aromatic compound which have same M by Z ratios?
He's asking that means how you are differentiating between aliphatic and aromatic compound with same M by Z ratio. He showed that.
Yeah.
Yeah. So.
Yeah. In the same, the next noble mass.
Actually, I think on this slide you see it well.
Yeah.
So actually, with the extractive electrospray, you really see. For example, you have C7H10.
Yeah.
So this is still very aromatic, and here you have, for example, C10H18. So this is a non-aromatic actually product. So these extractive electrospray are really able to distinguish actually these type of classes very well. It's not possible with the electron impact or electron ionization here, because you have too many fragments, and it's only possible actually with some of these new techniques.
So we are getting...
Okay. Detail can be asked later. Anybody else? Just one more question. Yeah, there. Stand up.
Good afternoon, sir. My name is Vikas. I am from IIT Bombay and I work on source apportionment. So
Can you speak a little louder?
Yeah. So what are the different source profiles you are using for, I know for Delhi we have source profiles, but what about in real-time source apportionment? How are you managing the source profiles for that study?
Yeah, so when we do the real-time source apportionment, we do first the pre-analysis. Yeah, we do a pre-analysis of some of the data that we have. And I mean, as a starting point, we use maybe, partially it's actually free PMF, but some components are constrained to some degree. But we don't constrain anything fully, so it's not a CMB approach or so. So we actually find, for these specific locations, we find actually the profiles that are important actually for these regions. So it's not any predefined. We just have, as a starting point, we use maybe some from the literature, but we find then in the first step actually those local profiles. And then we put these average local profiles, we put into the real-time source apportionment and run it. And we were not sure at the beginning if that would work out because it might change as a function of time and so on. But these correlations just show that actually, yeah, it works very well. But I think, yeah, one has to do it for longer terms and maybe for different sites to really prove that this is always working. I don't claim that this, will work right away. I mean, it needs still some development. But actually, these first results are super promising. I mean, that it actually works well enough, I think, that to actually explain, a lot of variability and so on.
Okay, thank you so much, Professor Privat. So in the interest of time, we will not take more questions. He is here, so you can interact with him during tea time or lunch time. So let us thank the speaker again. Just a second, Professor Privat, just a second. May I request Dr. Maya to give the memento to Dr. Privat? Please come this side. Yeah, thank you. Thank you. Okay, our next speaker is another well-known personality for aerosol scientist, Professor Dr. Griza Mokdik. He works in the field of aerosol optical properties. Anybody using athlometer must be knowing him. He is the head of the Center of Atmospheric Research and the Dean of the School of Environmental Science in the University of Nova Scotia and a research associate at Joseph Stephen Institute. He received his doctorate from the University of little difficult to pronounce, Ljubljana on photothermal and photoacoustic methods for investigation of highly absorbing and scattering samples. He has been a principal investigator in numerous international and national research and development projects in the field of aerosol instrumentation and laser devices. His work is mostly focused on the development of novel instrumentation for research of aerosol optical properties and application of this instrumentation, in particular measurement of black carbon and other light-absorbing carbonaceous aerosols. For 10 years, he was the director of the Research and Development SME. His current research includes the development of a direct method and instrument to measure aerosol absorption using photothermal interferometry. He studies the role of aerosol in the climate, source apportionment of carbonaceous aerosol for local studies in context of long-range transport, aerosol vertical profiles, and the methods for emission measurements. He mentored PhD students working on source apportionment, measurement of traffic emission, air quality models, and aerosolized mineral dust. He served as a member of United Nations EAC expert group of black carbon. With these few words, I invite Professor Griza Mokdik to give his talk.
Thank you very much. It's a pleasure and an honor to be here, and Iasta is one of the most interesting conferences to go to. I'll talk about the measurement of aerosol absorption coefficient. And measuring the aerosol absorption coefficient turns out to be exceedingly complicated. And the reason why we want to measure the aerosol absorption coefficient is because aerosols absorb sunlight and they heat the atmosphere. So they're a very important contributor to climate change, especially black carbon. And taking advantage of their optical properties helps us in source apportionment studies. And we define black carbon as mass concentration of highly absorbing carbonaceous particles. And if we measure them with filter photometers, like the ethalometer, then this is called equivalent black carbon because we measure an optical property which is equivalent to mass. Then we also want to measure the aerosol absorption coefficient because this is the quantity that tells us how much these aerosols contribute to the warming of the atmosphere. And we want to measure this quantity directly. The two are related, so the absorption coefficient is the mass concentration multiplied by the mass absorption cross-section. And the mass absorption cross-section is a property of aerosol that changes with chemical composition, morphology, and so on. And looking at how the absorption coefficient changes with the wavelength allows us to determine the sources of particulate air pollution. This dependence is exponential, and for instance, for diesel exhaust, it's very tame. The exponent is about 1. And for biomass smoke, it's about 2 or higher. For mineral dust, it's even higher. And we usually use filter photometers to measure this elemental black carbon. And we collect the sample on a filter, we illuminate the filter, we measure the transmission of light, we compare the transmission of light through a clean filter, through a loaded filter, and then we calculate the attenuation, and from the change of attenuation in time, from the time derivative of attenuation, we calculate the attenuation coefficient. And we can do this super fast. This measurement is non-linear, so we need to take into account this saturation, and this we've done by developing the ethalometer, which you can see outside. And then we want to convert this attenuation coefficient into absorption. But doing this, we need to take into account the filter. The filter intensifies the absorption because it scatters light heavily. And simplistically, we say that the absorption coefficient is the attenuation coefficient divided by a parameter which tells us how much this amplification of absorption is. So we have one number. Unfortunately, if we put white particles on a white filter, we also reduce the transmission of light through the filter. So there is some cross-sensitivity to scattering of this attenuation coefficient. And we need to take this into account because otherwise our measurement of attenuation can be slightly biased. So when we calculate the absorption coefficient, we divide the attenuation coefficient with this multiple scattering parameter, which is a property of the filter, and we need to deduct this small contribution. This factor is about a couple of % of scattering. So we need a reference measurement. We need a measurement to calibrate our filter photometers. And we need an additional measurement of scattering. And this is especially important at high single scattering albedo environments, for instance, for regional background sites where we have a lot of scattering compared to absorption. Because when we calculate the absorption coefficient as a function of the attenuation coefficient and single scattering albedo, the ratio between our measurement and the aerosol properties is this multiple scattering parameter
times this function of single scattering albedo. And we see that at high single scattering albedo, we are dividing by 0. So the ratio between the measurement with the filter photometer and the true aerosol properties is fairly constant at low single scattering albedo, and then at high single scattering albedo it goes crazy because this very small contribution, 2% of scattering, can contribute much, much more than absorption to our signal. So we have measured this in 2 places in Spain. This is a regional and a remote regional mountain station. And here we see the attenuation coefficient measured with a filter photometer divided by the absorption coefficient as a function of single scattering albedo in red. And we see this behavior where we overestimate absorption by a factor of 3. So we need a reference measurement to calibrate our filter photometers. And we do this with the photothermal interferometer. And the photothermal interferometer measures the same effect as the aerosols exert on the climate. We're heating the sample with a very powerful laser, and the particles absorb some of this light. And they heat up for about half a Kelvin. Then heat is transferred from the particles into the surrounding air. And this air heats up not very much. The density changes and the refractive index of this air changes. And then we measure the change of the refractive index as the change of the optical path in an interferometer. And the change of the optical path that we are measuring is about 10 femtometers. And the phase change in the interferometer is then the measure of the absorption coefficient. Because we have our interferometer, we have the in-phase and out-of-phase detectors, then we perturb the sample arm of the interferometer, and we measure the small phase change, which is proportional to the absorption coefficient of our sample. So measuring phase is a measurement of the absorption coefficient. And we've commercialized the instrument. This is the photothermal aerosol absorption monitor. It works in the infrared and in blue or green. And we've published the paper last year. So we are heating the sample. We have the temperature which increases during the on part of the laser, then it cools when the laser is switched off. This causes a change in the refractive index and a change in the phase shift. And we do this at 2 wavelengths. We do it in green and in the infrared. And we modulate these lasers with different frequencies. And these frequencies are then wavelength specific. And we detect only at these 2 frequencies. So we remove most of the noise. We remove all of the noise which does not have this specific modulation frequencies of the infrared laser or the green laser. And they're different, but they illuminate our sample at the same time. We need to calibrate our instrument, and we calibrate it with a gas. We calibrate it at low wavelengths in green and blue with NO2. The NO2 has a known spectrum, our lasers have a known spectrum, and we can calculate the absorption cross-sections for our laser source and for NO2. And we use a permeation NO2 generator which is traceably calibrated to primary standards. So our measurement of the absorption coefficient of aerosols is traceably calibrated to primary units. And we do this with this generator from the Swiss Metrology Institute, METAS. Then we have another measurement in the infrared. Unfortunately, there are no gases measuring in the, no gases absorbing in the infrared, so we need a well-behaved sample. And we are using nigrosin. Nigrosin is a water-soluble dye, which we nebulize and dry, and it makes completely spherical particles. So knowing the refractive index, the imaginary part, which is responsible for absorption, the real part, and the volume size distribution, we can use Mie theory to calculate the absorption coefficient. And then from the ratio of the absorption coefficient in green, where we have used NO2, and in infrared, we can transfer calibration from the lower visible wavelengths into the infrared. And then we validate this Mie model. And this Mie model is validated by measurements of nigrosin. We had 2 campaigns. And so using the measurements and the Mie model, the difference between the measurement and the Mie model in green is about 5 to 6%. So we are very happy with our Mie model to transfer the calibration from green into the infrared. And here we see the linear response to NO2 in green, no response to NO2 in the infrared, and 2 different calibration slopes for the aerosol absorption measurements for nigrosin particles. And the limit of detection for this instrument is about half an inverse megameter for 1 second time resolution. So we can measure also at remote places. The total uncertainty in green is 4%, in infrared it's 6%. The additional uncertainty here is due to this transfer of calibration. The uncertainty of the angstrom exponent is a combination of these two, and it's 9%. So we have an uncertainty of the measurement of the aerosol absorption coefficient around 5%, which is much lower than the uncertainty of filter photometers, which is about 30%. So using this, we can calibrate then our filter photometers. We can determine these calibration constants due to the filter. And here we see the calibration constant as a function of the volume mode, so the size of the particles. And we see 2 things. We see the first thing is that this calibration depends on the size of the particles, and it depends on the wavelength. So this means that the angstrom exponents determined with filter photometers are slightly biased compared to the true angstrom exponents of our aerosol under examination. We are using this in a standardization project to standardize black carbon measurement and to standardize aerosol absorption measurement. And the photothermal interferometry is a candidate for the primary method to measure aerosol absorption. Then we use this and a mass measurement to determine the mass absorption cross-section. And then we use this mass absorption cross-section to calibrate filter photometers for very different types of aerosols, from fresh soot, coated soot, and fresh and coated soot mixed externally with scattering materials. And then in the end of this project, we'll have a draft standard for the aerosol absorption measurement. So having this direct method, now we can use it to measure interesting things. And one of the interesting things that we want to measure is the increase of absorption due to coating. Because for climate effects, we want to know what happens when the aerosols, combustion aerosols, especially black carbon, are coated as they age and absorption increases. We want to know how much this increase of absorption due to coating is. And we did this at PSI in an aerosol chamber where we had different sources of aerosols. And what we see is that in a chamber we have a reduction of concentrations, and by plotting the absorption versus mass measured with an SP2, we get these slopes which are mass absorption cross-sections, and they're about 7 in the infrared and about 13, 14 in green. But then we age these aerosols and they grow. So from the fresh aerosols, we coat them, the size increases, and this increase is associated with an increase of the angstrom exponent. So aerosols go from black aerosols to more brownish aerosols, being coated only, so black particles coated with transparent coating. And in infrared, we can plot this mass absorption cross-section as a function of the coating thickness from the SMPS measurement. And we see this increase, which is fairly independent of the primary particle diameter. So the really important part of the enhancement of absorption, which is about 2 in this range of coatings, is the coating thickness, not the black carbon particle size. Also, it doesn't depend on the source. We can do the same thing in green, which is slightly more complicated because we need to avoid the generation of light-absorbing organics. And we see again that the increase of absorption is governed by the coating thickness, not by the primary core size. And when we plot the mass absorption cross-section as a function of the wavelength, we see that these increases of absorption, they're different in infrared and in green. So the difference of enhancement of absorption increases the angstrom exponent, which means that we are generating brownish aerosol which absorb more in blue than the black aerosols which were originally emitted. So as these aerosols age in the atmosphere, they become browner. We can also determine this change of the MAC as a function of the coating thickness for ambient measurements, where we measure the coating thickness with an SP2, and we have this distribution of the coatings in ambient aerosol, and we see the mass absorption cross-section, which increases for about 10–20% due to the coating. And the average coating is about 35 nanometers, which is less than our experiments. So to conclude, the coating increases absorption by a factor of 2 to 3, which is wavelength dependent, which means the angstrom exponent increases. And this is relevant for source apportionment, because we need to understand that we can generate also brownish aerosols, which are traditionally apportioned to biomass burning, also from fossil fuel combustion, which is then coated. And two, with the thick coating in the laboratory and from ambient measurements, we see that there is an enhancement which is between 10 to 20% or a factor of 2 to 3, which needs to be input into the climate models. Because the climate models do not treat this very well, because especially for places where we have a lot of scattering, the indirect effect is super important. So I won't read the conclusions. We have a new instrument which allows us to measure the aerosol absorption coefficient directly. It has no artifacts, and it has a very low limit of detection, which means it's useful not just for laboratory measurements, but also for ambient measurements. Thanks a lot.
Thank you. Thank you so much, Professor Momdik, for keeping the time also and for such a informative talk. So there is a time for a few questions, pointed questions. Yeah. Yeah. Anyone? I think everybody is very clear, whatever you presented.
Hello, sir.
Yeah.
Hello, sir.
My
name is Tejas Rathod. I wanted to just know that did you find that this enhancement is independent of this fuels, like it may be parameterized in terms of BC by OC ratio? Because I have seen some study that it may be independent of fuel type.
So we've used straw burning, which is a simulation of a very inefficient, for instance, agricultural burning, which is relevant in this season in the Indo-Gangetic Plain. We've used wood burning, which is a good model for the type of mixture of black carbon and organics that we find in Europe used for domestic heating. And we've used an Argonaut burner, which is a model for combustion engines. And we've seen different morphologies for these different sources, and there are different sizes. And we have seen absolutely no dependence of the enhancement of combustion on the source itself. We have seen the dependence on the coating. So it's important, of course, which pollutants are co-emitted, especially in gas form or the organics, which then are aging the atmosphere and decode these particles. But once all of these emissions are mixed, the source itself is not so important than the mixture. So the compounds, the organics that coat our primary particles are the relevant organics. It really is just a matter of how many organics we manage to get on our primary particles to enhance the absorption. And of course, if they're not transparent, the enhancement is larger. But so the chemical composition matters. But in principle, it's the coating thickness that is the most important parameter. And this needs to be put into the climate models, because the climate models do not take this into account properly.
Okay, thank you.
Okay. Anyone else? Yeah.
Sir, I have
Last
two
question.
questions. First is this absorption coefficient. So you have used 532 nm laser and 1064. So this 532 is within visible region. So if in the aerosol there are some organic compounds, those are chromophoric, which absorbs in this region. So for those type of compounds, how this linearity is maintained? And the second thing is, if in this aerosol,
can you keep the mic close and speak a little louder?
Should I repeat the first question?
Yeah.
So my first question is regarding the absorption of this 532 nm laser. So in the most of the organic aerosol, in the aerosol form, they are chromophoric in nature. So they absorb this 532 nm laser. So the limit of detection and the linearity, how it is maintained for those type of compounds. And the second thing is the aerosol composition, the chemical property changes with RH and temperature. So suppose at particular RH, I have taken the absorption at a higher RH where there are more number of water molecules. So they will absorb the 1064 nanometer higher region. So that will change the whole result. Then with RH, how it is being taken care for those kind of stuff.
Thanks. So the first question is, you want to make multiple wavelength measurements so that you can characterize the aerosol absorption dependence on the wavelengths. And the organics absorb at low wavelengths. In the infrared, the absorption can be attributed only to black carbon. So that's why you want an infrared measurement, because this is easily converted into black carbon mass. At lower wavelengths, then you need a two-component model where you extrapolate from the infrared, and the difference between the extrapolation and the measurement is attributed then to organics. Now, in terms of the ambient conditions and the influence of ambient conditions, especially volatility of organics and the adsorption of water onto the aerosols, this is the only instrument that can measure the dependence of absorption on the humidification of the aerosols. You cannot do this with filter photometers because water interacts with the filter. You cannot do this with photoacoustic measurements because of two reasons. One is that the photoacoustic signal depends on the size of the particles, so you need different calibrations for differently sized particles. And two, speed of sound depends on the amount of water, so you need to calibrate your photoacoustic instrument depending on relative humidity. So you need to correct this. In a photothermal interferometer, you're constantly monitoring the interaction region. In the photoacoustic instrument, the photoacoustic wave goes away from the interaction region before water recondenses, so you have a bias. In a photothermal interferometer, you see the desorption and the adsorption of water molecules onto your aerosols. So you're able to measure this without a bias.
Okay, thank you. So let us thank our speaker once again. Yeah, now as a token of appreciation, may I request Dr. Sapra to give the memento to our speaker? Please come this side. Okay, let us move on. So another talk, again, highly renowned atmospheric scientist by Dr. Prabir Patra. He did PhD from Physical Research Laboratory, PRL, affiliated to Gujarat University, Ahmedabad, and MSc from Jadavpur University, Kolkata. After a brief spell of about 3 years at IBM India Research Laboratory, Delhi, he has moved to Japan Agency and Marine Earth Science Technology, which is known as JAMSTEC, Yokohama, Japan. His primary research interest is to estimate sources and sink of greenhouse gases and ozone depleting substances using atmospheric chemistry transport models. He has deep interest in air pollution and human health, which is an urgent issue in South Asia region. He is currently leading Akash project at the Research Institute of Humanity and Nature. He is a recipient of Horuchi Award 2016 from the Meteorological Society of Japan for an individual who has made a significant contribution in interdisciplinary fields related to atmospheric sciences. He has published more than 175 peer-reviewed articles. His team collaborators contribute to budget of CO2, methane, and TUO of the Global Carbon Project under auspice of Future Earth and other Japanese and international research activities. He is contributing author of IPCC AR5, lead and contributing author of IPCC AR6 of Working Group 1. He is serving as an editor of Nature Communication, Scientific Reports, and many other journals, and he is steering committee member of Japan IPCC Working Group 1 office at JWA, GCP, RECCAP2, OCO2, 2 and 3, COSAT, etc. With these few words, I would invite Professor Patra to give his lecture.
Thanks, Neeraj, for this wonderful introduction. It's too much hyped, I guess, but anyway. And one thing I would like to say from the beginning is that I am new to the field, so I may make a lot of mistakes. But yeah, so I will just talk about the PM 2.5 and air pollutant observations we have been making in the area of biomass burning and crop residue burning, basically, in the Punjab and Haryana and Delhi region. So with that, I'll just go to my talk and introduce you the Akash project. So, and this is different from the, so far what you have heard. So I am working in this project in the Research Institute of Humanity and Nature. And this is a transdisciplinary institute, which means that we must work with the people on the ground. If you're talking about crop residue, then you have to work with the people who are involved in the crop residue burning. You have to be involved with the people who are affected by the crop residue burning, etc., etc. So that's the kind of transdisciplinary research we have to do in this institute. So in this case, then we have like 3 working groups set up because it's so diverse. One person cannot handle all the things. So each things are like managed by different group of people. And we do this kind of field surveys, which actually where people go on the field and they talk to the local residents and understand what they are constrained, what they are doing, and why they are doing. And that's kind of a socio-economic point of view. And then we also have, in this case, remote sensing people, who are like remote sensing or atmospheric observation people, which are kind of, I am in part of that. So we do remote sensing, atmospheric observations, which I'll discuss here, and try to scale up the system and of the field surveys and with atmospheric observations. And then within the working group 1, we have these people who are actually working with the people who can think of a solution to the problem. Because we can study this, but then we also know very basic things which can be implemented that can reduce crop residue burning. And since I just actually came back from COP last night, so in COP I discussed about the co-benefits of air pollutions and greenhouse gas reduction mitigation targets. Because there are some things we talk about in the COP is that co-benefits and like carbon capture and storage. So what we say in this case is that the crop, when you grow the crop in the field, you are assimilating CO2 from the atmosphere. And that basically is doing the capture part for your research, for your implementation. Now it is that we are giving it back by burning. That means you are losing the residue which you have actually captured without using it. So we can have solutions. There are ways you can manage the crop residues where we can actually make biochar, apply to the field, store it, or use a biofuel, or even one thing we are proposing, the crop diversification, so that we don't have to produce a huge amount of crop residues from the rice straw. And then obviously we need to link it up with the health, and what we are doing is that we talk to the people, develop the awareness, why they are, how they're affected by air pollutions, and what they could do even to solve some of the things in their own backyard. So with that background, I just also go slightly more here, is that what is happening, and we have been reading a lot on the news. I think everybody knows about it. And the thing is that we discussed the crop residue burning to be another main cause of the air pollutions in Delhi, as there are some linkages at least. And that we saw it by the observation from atmospheric remote sensing, which is from MODIS in this case, is the state-wise total fire counts, which is shown as the blue bars. And we also use another proxy for the crop residue burning, the burnt area, which has been also used for the emission inventory studies. And we try to see that whether they are agreeing to each other or they are not agreeing to each other. And then we find a very nice scenario is that it has been increasing in the year 2000s. And when the mechanization of the farming in Punjab happened, where you have electrifications and new crop variety came out, and then we had the Water Prevention Act, and this kind of continued to increase the PM2 crop residue warnings in Punjab and Haryana until about 2016. Then we have implemented the Natural Green Tribunal Act, and then which is we have to try to stop the transboundary pollution. And then you can see that there is an effect of the policy that the crop residue burning basically going down with time, and we are in the also these things. These policies can be really seen for the remote sensing. You can also see when the Water Act was implemented in 2009, when the crop residue burning was happening much earlier in October, but now once you have delayed the cropping cycle, the crop residues are produced later, and crop residue burning also happening later. Also, we have a thing I will show you. There's a long variety grain which we use now in the production system. As I said, that we make field studies, so that our people go to the field and ask the farmers what are they doing with the crop. Then if you take a statistics, and you can see that how much crop residues are burnt in which, for example, district. And you can make a map just by survey. And this looks strikingly similar to what is from the remote sensing, the MODIS or BIRS or anything else. Then you ask people, what kind of crop are you growing on your field? And that is very important because Pusa 44 is a long grown phase crop, and it's a high yielding. So people have been changing to this crop since 1993 or something, 1995, because that is a rice crop produced for the high yielding variety. And these are supported by the Indian government minimum support price. So all the economics and everything comes into this business, why these people are growing this crop here, and why there is an intensity increase of burning in the year 2000s. And then these things are being put by the economic models with ERI collaborators, and then we are trying to make decision making for different things. And second thing, we also do like a health and surveys and ask people like what you think about the air pollution in Delhi, what do you think about the air pollution in Punjab. I'll go quick over this, and what do you think about the air pollution's health effect on your family. And we can make these charts for each district and see that there is a link between in how they live and the exposure to the science and the newspaper, for example, or the experience they feel on the field. For example, here, air pollution about Punjab, people feel very strongly when they're living in the high burning fraction areas, which means that they really experience it, that air pollution in their at home. So that's very important. And then now we want to prepare some numbers for each region. So this is a kind of things we did from our project is that, is there a time counting here or no? We just, anyway, so no, not now, but I just want curious. Anyway, so then we just make these measurements, and then last year I also, and this year, and then the way we did a network of the very cheap, low-cost sensors, which is called compact useful PM2 sensors, it's QPGs, we put 30 of them in the region of sources, in the Punjab, Haryana, and Delhi. And the region where you put also the hotspot numbers, you can see in this area, it covers, not covered so well by the existing network. And so to fill up this gap and to track this movement by the same set of sensors, because the calibration is an issue and other things, so I think using same sensors, well, we calibrate the sensors in Japan first and then transport and install in the field. And then we also did a similar network of observations in 2023. Just finished the crop residue burning season. We have slightly revised them. And then this is a kind of a plot we have already shown in this paper, is that we can plot the PM2.5 concentration over Punjab sites, at Haryana sites, and at Delhi sites. And there's some limiting, some linkage to the meteorological conditions, which is rainfall or the fire counts. And one thing you'll notice to the very primary that we have a very big peak in the PM2.5 concentration in Punjab in about 900 micrograms. And that time we had a very low fire counts in Punjab. So this is kind of a thing is that I will show you that it is a kind of a cloud cover affecting the remote sensing observations. And then we can explain these peaks of PM2.5 in the source region and how they get transported by this kind of plot. Here you can see that this map is converted into the daily mean PM2.5 concentration on a map, and then the size of the symbols basically tells you how big is the PM2.5, how is the PM2.5 concentrations, and then the rainfall is shown as a bluish color, and then fire counts are shown as a blackish color. And we can now see the movement. So this peak from PM2.5 from this area came directly to Delhi, and you can see the high PM2.5 concentration in the last year in crop residue burning seasons, about going up to 400 microgram per meter cube. And then other days when you had a very big peak in Punjab, that did not come to Delhi because it has a different wind patterns, and we can see all these things nicely in this kind of map measurements. And then another day when the Delhi had a high PM2.5 concentration, it came actually from this side again. So these are kind of events we have captured. And so now we can actually do the whole analysis and from where they go and where they come from. These are completely, I think this is where we need to work much more in that to understand how much they come and from where they come. We need a lot of network of observations. And the one thing I'm mentioning is that the PM2.5 source, how you define source in this case. So here, if you see that, we are showing that hourly PM2.5 concentrations at event 1. I showed the very high event on PM Delhi, and then another event in PM2. And then when you have a very high standard deviation between the different sites, the variability is very high, which means the source, because the source varies very quickly. But when you take the source by the plume transport, if they get more organized, then the PM2.5 variability between the sites are very less, because they are passing the same plume over the sites. So this is kind of a thing we could actually show in this case. And then I was mentioning also the measurements from the measurements problem from the satellites. And if you see this peak period, we see that very large cloud cover in these areas, and we could not see from the space if you have done only believing on the remote sensing measurements. And similar, it is much worse in these peak regions because Punjab, Haryana, Delhi is not covered by satellite observations because of cloud cover. So this is why the surface observations are very, very important. You need to make measurements on the ground. They're much more precise if you can calibrate them, this discussion of the calibration. And so they're very helpful for your understanding of continuous development of the PM2.5 concentration. And coming to this year's result, we put again similar kind of plot, and you can see that this is the kind of Punjab regions, and this is from the Delhi regions. We did not show Haryana here. I think that there's some Haryana figure also here. So what you see here, this is the PM2.5 concentration Delhi means on the top two panel, and the lower panel is the wind directions and wind speed. And there is some linkage, which I discussed before, that directions makes a lot of difference in the PM2.5 concentrations. And what we see extra in this plot is that we put the government policy on the background, which when the graph 1, graph 2, graph 3, and graph 4 came into the action. So actually PM2.5 concentration in Delhi and many sites were keep going up until the graph 4 was implemented, and then you can see the concentration going down. And there was and this is a Diwali day obviously, and marked this one. And in this case we can also show you that to understand some bit of, I said that we make measurements of CO, we make measurements of NOx, and we make measurements of ozone or OX in this case. So here I am plotting some the PM and CO concentrations with day and nights averaging. So what you see in this plot, the PM2.5 concentration in the night time, which is dark black color, is high in the Punjab region. It's a Bhatinda, which is like a southwest of Punjab, where a very huge crop residue burning occurs. And in Delhi, it's like CO concentration in the night time is much, much higher. So this tells you about what is going on in the source and the characteristics. One is that it is primary PM2.5 produced in the source locally by the crop residue burning. So in nighttime is the concentration goes up. And in the Delhi region, it's more like a vehicular emissions, and then PM2. And then CO is much higher compared to PM2.5 directly, if you see the direct emissions. So here the gap 4 basically works. It slightly take down the Delhi PM2.5 concentration. You can see the stepwise changes. And we can do similar things for this. But what was also I wanted to show you here, because I think up to around this year, we see a lot of newspaper and articles talking about the bringing artificial rain to Delhi. And that time we have been thinking, okay, the PM2.5, and then maybe we'll have an artificial rain. But then I think our rain gods, all of them helped. This rainfall happened. And then you can see the PM2.5, how drastically it's changed in just one day. And it remained slightly low in another day, but then again it goes back with all the activities back into the business. So the rainfall helps if they can produce artificially or by our God. And then we are also doing the analysis to show that the PM2.5 concentration, when they're emitted from the source region, how much they can go and where they can go. One thing, we are doing this kind of analysis, and then we do this kind of animations. So this is a PM2.5 emissions in our case, a kind of a proxy on one day of 2020, I think it's 1120 here. And then we transport these emissions for 3 days in the system. And you can see that this day the PM2.5 went towards south and east side. But on another day, the PM2.5 emitted for all these regions went towards bit south and west. So these all things have a lot of implications, like how you associate the crop residue burning with the Delhi air pollutions. So then I think I will skip many of the things, and then I asked that we need a, and we are putting this kind of observations data and the analysis on the website, and then we can actually download them, and you can also get in touch with us to get the raw data. So I think all the plots, many animations, everything is available on this place. I think Neeraj is up with the microphone, so probably time is up. Thank you very much.
Thank you. Thank you so much, Dr. Patra, for such an informative talk. So I'm sure there will be some questions. We can have a few. Yeah, Dr. Saha.
Wonderful lecture, Patra ji. बहुत अच्छा, सुंदर. Actually, just by thinking is that we talked about the PM10 concentration, increased PM10 concentration over Delhi and NCR. But if you see the concentration of pollutant, mass concentration, it is PM10 dominated. Delhi is PM10 dominated, not PM2.5. This is the thing just I wanted to highlight. Number two is the meteorological factor. I have done one analysis for the entire states of Delhi, Indo-Gangetic Plain, the meteorological condition. The NCAP, the conditions, the vision that NCAP emphasizes, it will never met The Bihar will never be able to meet the requirements. Delhi will not be able to meet the requirements. Chandigarh will not be able to meet the requirement because of the meteorological factor. Beksab is here. And Punjab, Haryana is on the right side. They will be able to meet the requirements. Uttar Pradesh, it will meet the requirements. And sometime the West Bengal will be meet the requirements. In that circumstances, whether should we not review the NCAP strategies or not? This is my one simple question from Dr. Patra, please.
This is not a simple question. Yeah. So I think I think this one probably one of your statements, city we picked up is I think Chandigarh is here. The blue green line you see here that is Chandigarh. And Chandigarh really actually did very well this year. And then to explain that, we have been just struggling, why Chandigarh? And Chandigarh is here, by the way, who doesn't know what is Chandigarh. And Chandigarh is, every day, Chandigarh has a low PM2.5 concentrations. And that's also obviously helped by the meteorological conditions because the fires are happening a bit south and west of Punjab. And Chandigarh had, this year, every time they had a wind coming from the northern west side. Chandigarh really made this year's PM2.5, and that was very confusing to us in the beginning. Why Chandigarh is being so safe from this, all the crop residue warning in Punjab we are talking. So we can meet in the criteria. And I just came back, I said from Dubai, right? So you can actually, Dubai is not a very green place. It's quite dusty in terms of like if you just go outside of Dubai. Similarly happened, I went to Sharm el Sheikh last COP, also like in the desert, middle of desert. So they are still very clean in the city. You can see the horizon very dusty, but the city itself is very clean from the PM2.5. It's not very clean, but 50 microgram per meter cube, PM2.5. So which means that there are ways we can actually reduce the PM concentration within the living area of the cities. It is possible. We cannot really say that we cannot meet a certain extent. Like I would say that 40, 50 microgram at maximum concentration can be maintained, but you need a very, very effective policies. One of the things I was just mentioning was the GRAP thing. So the GRAP 4 actually really helped you to bring down the Delhi air pollutions in this case. I don't think it's just the rainfall here, but the GRAP itself was acting before when the GRAP 4 came up, the PM2.5 went down in Delhi. So you know what are the kind of sources. There are many, I think there are many local sources, so that by implementing GRAP, you can reduce Delhi air pollutions. And similarly, I think many other places we can actually make, and then obviously NCAP has to play a very major role in this case. And as I mentioned, that we need more people to come together and work and think about it. This is the right opportunity for us, I think. Thank you.
Yeah. So Dr. Baig, yeah. Patraji, a good presentation. There too, one specific comment that when you are having a 24-hour average, you are always finding the concentration of PM2.5, PM10 much less in the area when there is intense fire as compared to Delhi.
Yeah.
So I think in your graph you are showing most of the time these things, but this is what is the real observations which we know about that. One. Another thing is that you are showing the wind speed and direction, I think, near the surface. But what is the level in the model which you feel, certainly it is not through the surface. What is that millibar level where normally the transport takes place from the burning area towards Delhi? So these are the two things which...
Yeah, this is why actually we are looking at this kind of animations. This is a whole three-dimensional model plot. And we are looking at the surface concentration. So any concentration which is emitted is taken up by the winds and everywhere, and it's okay, how they are transported. So
what is that millibar level? Any
no,
idea?
this is what I'm showing here is at the surface level. So you can see that this is everything what comes down to the surface. And obviously they come from very, very high, different heights, depending on the conditions. It's never in the fixed height. So every day that the height changes. And you can also have slight pyroconvections, everything else is put into the model, you get these things. This is not a full chemistry model, it's a flex part black carbon model. But we are also developing the full chemistry model where you can actually put emissions, see the chemistry happening, because cooking and transporting and cooking of the air pollution, secondary air pollutions are a very important component of this, which is secondary pollutions are not taken into account here. So I think that we need a full chemistry models to attribute.
So my just one suggestion is that if you can come up with a parameterization that what is the most favorable congenial conditions in terms of a wind speed, height, and the direction. Direction is anyway north-northeast, that's okay, towards Delhi. I think that would be a very good empirical model.
Yeah, thank you. We'll try that, yes.
Okay, thank you. No, Miss, now we can talk after, during the lunch or tea time. So let us thank the speaker again. Yeah. And may I request Dr. Beg to give the memento to Dr. Patra. Wow. Thank you. And now is the time for the last presentation of the session before our lunch. So this presentation is again by a very well-known person, Dr. Santu Ghosh. He is working on aerosol and health part. He earned his bachelor's and master's degree in statistics from West Bengal and PhD on biostatistics in environmental health from Sri Ramchandra University, Chennai. Presently, Dr. Santu Ghosh is an associate professor of biostatistics, specializing in observational and clinical epidemiology. He has 18 years of experience as a lead biostatistician and worked in numerous nationally and internationally funded projects, including the Global Burden Disease 2010 project and the WHO guideline for indoor air pollution. His core research area of interest are air pollution, epidemiology, and public health nutrition. He served as a resource person for recommended dietary allowances 2020 by ICMR and a statistical consultant for UNICEF for CNNS data analysis. He is also closely involved with NIN Hyderabad ICMR for multiple research projects related to nutrition, including ongoing diet and biomarker survey in India, which is called DABS-1. He is also a steering committee member of CAFR India, joint venture of AIMS and IIT Delhi, funded by Health Institute from Boston. He has more than 90 peer-reviewed publications in national and international journals, and many other things. In interest of time, I will not speak much and request Dr. Santu Ghosh to give the lecture. The pointer is here.
Thank you for the introduction. Okay, I'm almost one of the end user of this conference. So I'll talk about the health effects that evidence from our own country, India. However, there are several, evidences globally available for PM 2.5 or, PM 2.5 component and health effects, but very limited in India. And this presentation, we want to see how actually we are stands with respect to the health evidence of air pollution effects in our country. Okay, so if we look at the air pollution, then air pollution been a major concern for health in India across, more than 2 decades. And there are a few studies recently published based on, though these are the studies that mainly utilize the Western health and air pollution effects evidence, very limited from India. However, there are estimates around 1.6 million deaths in India were attributable to air pollution, out of which 17.8% of the total death, which is actually 17.8% of the total deaths of India, that is Lancet Planetary Health 2021. And then even there are 25 cities studies that shows that there was an association between PM 2.5 and COVID-19 death. And in terms of the economics, if you look at that, that recently in the Lancet Planetary Health 2021 reported that the death and the morbidity attributable loss to the air pollution is around 28.8 billion and 8.8 billion dollar respectively in India 2019. Keeping that in mind, if we look at the different health effects that may happen due to air pollution, that these evidence are mostly I highlighted those that the causal association is already established, but there are few newly emerging issues that are coming that are linked to air pollution, but it's still in shade, so they are not well established so far. So if you look at the respiratory, the irritation of the nose, throat, lung, coughing, wheezing, asthma, and COPD. On the other hand, the cardiovascular aspects, heart attack, stroke by causing inflammation and oxidative stress. Then, cognitive impairment, Alzheimer's disease, Parkinson's disease, etc. Then reduced fertility, fetal growth restriction, preterm birth, low birth weight, lung cancer, and some eye and skin irritation and the complications that are so far we observed globally. But if we look at where we are at present in India, the recently one study by Rajak and Chattopadhyay from IIPS, in 2019, they reported almost 59 air pollution and health studies. But most of them, if you look at our cross-sectional time series or case studies, very limited are cohort studies. So those evidence can be considered as the evidence of air pollution and health effects, but it's really, as nothing was used just to quantify the association, it would be difficult to take forward for any policy level implementations. So that's why we did more studies on the causal aspects to impact exact association, to estimate the exact association of PM 2.5 in India, especially because we are in the higher spectrum of the air pollution. What we saw in so far in Europe and America, that air pollution is not at all that level where we actually everyday experience. And if we recall the exposure response association between air pollution and health, it's not linear. So it's a bit quadratic. So as a result, we are in a higher extreme of the air pollution exposure. The association could be different. So in that aspects, we really separately need to quantify. However, not for the evidence, but for the quantification purpose, it is very crucial. And next, I'll focus on few of the most of the studies that are conducted after 2019 review work that Chattopadhyay and others did. This is the Lancet Planetary Health that is mentioned almost 0.98 million to PM alone, the death, premature death, out of 1.6 million that they reported. And recent study by Selvi 2021 compared self-reported respiratory symptoms and school-going children between, this is not exact PM 2.5 and the respiratory symptoms, but they compared between two cities can be considered, as Delhi was the high pollution, whereas the Kottayam and Mysore, Kottayam is Kerala and Mysore is in Karnataka. These two cities, the PM 2.5 level during that period was reported around 15 to 30 microgram per meter cube, whereas Delhi was 79 to 128 microgram per meter cube, and they observe a positive association. Even the adolescent children living in the polluted city of Delhi and shows the higher prevalence of asthma, respiratory symptoms, allergic rhinitis, and eczema that's strongly associated with high body mass. Body mass is another factor. I'm not going into details. Then if we look at the lung function, there are some studies, however, very scattered, but not so strong evidence so far observed from India. But that Ranjini, this is another South Indian cohort, that they have reported a positive association between PM 2.5 and the indices of the pulmonary function test. Similarly, another study, that in Jane 2023, they also found the positive association between air pollution, PM 2.5, and the that is in these two, it's not exactly PM 2.5. Again, they compared between two cities, one with Delhi and other is the Pahalgam, that in Uttarakhand, that level also around 30 microgram per meter cube during the period that they conducted the study. So they showed a positive association, higher impact in Delhi than the Pauri. And then COPD, there are some studies in 2021 that they reported a positive association between, there is no exact PM 2.5 and COPD association from ambient PM 2.5 is concerned. There are some indoor air pollution studies that reported the association of COPD and PM 2.5. However, the PM-induced oxidative stress seems to be the major player in this, but the molecular mechanism is still not clear, need to be established. And the ARI is, one of the issues that recently few studies that have reported, but these, the two studies that I will talk about, they are mainly, cross-sectional data, the NFHS4 data, both the studies. One is NFHS4 alone that was done in India, and another one is the whole DHS survey, the globally one work was done. But both of these studies almost showing similar effect. And here, this study, they reported around 0.6%, increase. On the other hand, 1 microgram increase in PM 2.5. And then the other study that I talk about, that is the whole DHS data that was used globally. And the global estimate surprisingly also found almost the similar, the 1.06, if you convert into their unit, what they reported, it is 0.6% per 1 microgram per meter cube, or 6% per 10 microgram per meter cube increase of ARI. So these are the two studies, but there is no cohort as such. One of the cohort that I was involved, but that was not yet published in Chennai. But these evidence is not so strong so far, but it is only a cross-sectional evidence, cannot be considered as actual impact of air pollution, is need to be validated by a cohort study. And we talk about cardiovascular illness, again, that same South Indian cohort, the Ranjani et al. 2022, they reported the association, CIMT is the carotid intermedia thickness, is one of the considered to be, it's not so strong, but it's considered to be a early marker for coronary artery disease. And they found a positive association. However, that association was little bit precision-wise compromise, but they reported a positive association between PM 2.5 and CIMT, which is a marker for coronary arterial disease. In the background of, if you can, think about it, the premature coronary arterial disease, one of the, very emerging concern for Indian health community. People are getting heart attack, age of 30 to 40, 50, below 50. And that are really a major concern. Air pollution is not the only responsible, but could be one of that. However, other lifestyle-related issues and stress, occupation-related issues are there. And hypertension and air pollution, also there are some evidence, one from the Prabhakaran et al. From PHFI, and another study that happened, Kalpana, my guide, was involved. So they have reported a positive association with, hypertension and air pollution, PM 2.5. This area is still not so strong, the cognitive health and air pollution. There is no direct studies of PM 2.5 and the cognitive health. The neurodevelopment is one of the emerging, issues and very important area for environmental epidemiologists to take on some research in this area. But whatever the evidence that are there, one is this is the cross-sectional survey. If you can, the longitudinal aging study in India, they show some association of the indices of cognition according, and the other, that is fully, indoor air pollution, but still this area is still not so strong in India. And recently one study, they also found the child development is also associated with PM 2.5, though it's based on, again, NFHS 4 data and the model PM 2.5, but shows that the stunting is increased by the increase of air pollution. The reproduction health and air pollution, the growing evidence in India are coming up, for this part of this study from multiple cohort studies. One of the study that is showing that there is a positive association, and the association is not as such linear with the PM 2.5 birth weight or low birth weight. And another cohort study where I was involved, that shows almost 4 gram reduction in birth weight for 10 microgram per meter cube increase in PM 2.5. This is one of the cohort studies, so it's considered to be a strong evidence. And recently another cohort by Kalpana, it's a clinical trial. So the LPG trial was conducted to see whether LPG can reduce the low birth weight. However, there are 4 countries study, but the first work that they have shown just LPG without LPG, they didn't establish this association. However, when they analyze the data as a observational study considering the PM 2.5 actual exposure and low birth weight, they found some association, but even though in the same region, what we reported around 4 gram per 10 microgram per meter cube reduction, but they reported it is around 14.8 gram reduction per 74.5, which is coming around 1.8 or close to 2 little reduced, but they found some positive association. Surprisingly, it was not observed when LPG and no LPG was analyzed. So that is little misleading. However, it was the high-end publications. And another recent evidence that came from the publication of PHFI, that the metabolic disorder and PM 2.5, they reported that the fasting plasma glucose is associated with the PM 2.5 exposure, and even the T2 diabetes, type 2 diabetes associated with PM 2.5 exposure, and this association is not linear again. They found non-linear association, which is quite obvious if you really keep the exposure response association in mind, so far that observed globally. And I'll focus a few minutes on some short-term impact or the acute effect. That means this impact is not the impact of the healthy individuals, rather those who are compromised in health, and what could be the impact of high air pollution exposure to them. So this particular study, or this type of study, actually helped Europe and America to set up an intermediate policy to reduce the air pollution. Later they confirmed by the cohort studies, but the time series study is one of the important quickly done studies that can help to find find the association or the evidence of the association of PM 2.5, the aerosol or the PM 2.5 and its component on health. These are acute though, but very quickly and less expensive study based on the secondary data. So that's why the evidence is not considered to be very strong. However, So this is one of the PAPA initiatives, that study that is even the, you can consider these two studies are the first India, not the actual first time series study, but the whatever the current trend of time series study, the whole protocol that was followed first time with these two studies funded by the Health Effect Institute, Boston. And then after that, there are few studies that also conducted, and not only the all-cause mortality, but also the hospital admission, and initially PM10, and then, first time we established some association with PM2, acute effect of PM2.5 in Varanasi, and then even, later we tried, these are the Delhi study, that one of the important study, I would say, these guys from Ahmedabad, they reported multi-cities effect, and even if you look at the impact, if you look at the lower the pollution, higher the impact, acute health impact. If you look at the Simla, it is 1.36%, compared to if you look at other Hyderabad or Mumbai is 0.8, 0.2%. So the acute impact would be much higher if sudden peak observed in a relatively low air pollution area. So that is what it observed. And even we tried with the satellite data, satellite PM2.5, and we observed the same association, the Delhi, that is PM2.5, is 0.52% increase per 10 microgram per meter cube in the all-cause mortality. However, all are all-cause mortality. That the same contemporary study was done but a different exposure model by the PHFI. They also found almost quite similar association in Delhi. And they later, we conducted one study along me and Sagnik, the association of PM2.5 components and all-cause mortality. 2 minutes, yeah. So PM2.5 chemical components and the all-cause mortality, we find varying impact, the differential impacts of different components on all-cause mortality. If you look at the impact, that is, if you PM2.5 impact is 2.6%. On the other hand, there are nitrate, ammonia, nitrate, and other, if you look at the ammonium, the anemia, these things. Even look at the other part that where we imputed the series, and that is much more precise estimates. Even it's higher, as more than 2.5 times higher in nitrate, if you look at that. So there is a differential impact observed. So PM2.5 may underestimate the actual impact as far as the acute impact is concerned. Then the recent evidence that we observe for anemia too, that the under 5 anemia as well as women of reproductive age anemia was, we found association between PM2.5 and anemia, and even in this WRA we model the different PM species and associated with anemia prevalence, and we found the sulfate, black carbon are the more strong association than some other organic and dust. And even there is another recent study where we explored the child health and different PM2.5 species. Here also we observe varying impact of different PM2.5 species. Nitrate, elementary carbon, and ammonia are the more, the association has more association with child health, like anemia, the low birth weight, as well as ARI. So if you look at that, the main takeaway, even here we estimated the cumulative effect of these species and compared against PM2.5. If you look at that, the actual PM2.5 mass, if you compare, there it's showing that if you look at the anemia, ARI and low birth weight, it is 10%, 11%, and 5%. But when all species cumulative impact was considered, it observed 49%, 35%, and 23% increase in the respective health problems per 10 microgram per meter cube. So in conclusion, I would say the evidence are growing up day by day, but still some area that need to be focused. That evidence are very, very, little, like, neurological health, the emerging concern of anemia and the cardiometabolic disease. And the other part that I would say that the inflammatory pathway is the most common explanation of the effects of air pollution and health by the oxidative stress. So antioxidant-rich diet could be a potential intervention. Research should be undertaken in a country like India, where sizable population is suffering from malnutrition. And reduction of air pollution at a level of at the level where it's considered to be safe as per WHO is almost impossible in next few decades in India. So we have to find the alternative strategy how to fight with this air pollution and prevent from health effects. Thank you.
Thank you, Dr. Ghosh, for such a. Okay, so there is a time for a few quick questions. Yeah, Dr. Sabra.
So after looking at the presentation, it looks like breathing is the culprit. So the only strategy I can think of is stop breathing. But jokes apart, it would have been nice if in each of your studies you had given the cohort size. That gives us some confidence on whatever correlations are being drawn, whether they would be really acceptable or not acceptable. For example, when I was seeing the PM 2.5 or PM 10 being associated with HB1AC, I do not understand the biological mechanism because I'm not a biologist, but I'm not sure how this works, and it would have been nice to give, if there is any explanation why this kind of a correlation is feasible.
Yeah, as I mentioned, that most of the association is through inflammatory pathway. So there are still research is required, how this, the metabolic syndrome, anemia, that are very, gray area, and that need to be explored. More toxicological studies are required to understand actual pathways. That particular aspect, that HbA1c and other things, it's still not clear, actually, that I can say you that this is the actual pathway. But it is expected that, it is inflammatory pathway, but actual things, even I am not a biologist, so can say you something. But
yes, sir. I have a very much related question which madam has asked. Most of your observation have shown just the data that this observation you have seen, like you have seen anemia, you have seen childhood related abnormalities. In addition to that, you have shown in one slide cardiovascular related diseases. So how sure you are it is because of the only this PM 2.5 air pollution only? Have you encountered other part, like what we are eating directly, what we are drinking directly? They are more related to the overall health effects. Breathing is one part, but we have a closed system. Lung is a closed system. Whatever we breathe, rarely it goes to the blood circulation. But whatever we eat, definitely it is going to enter in your blood circulation. So how sure you are that what effect you are seeing, it is because of the breathing, not because of the part what we are eating or drinking?
Thank you for this question. Actually, it's 20 minutes. I had to cover so many studies, and that also after 2019, when I didn't touch at all what, Dr. Chattopadhyay, published. So, yeah, that is a cohort study. What I mentioned, it's a cohort study, and all those factors that you are telling, they control it. Few components are controlled in the design, and remaining the statistically controlled. They capture the diet. They capture stress, okay, and other causes that might, be a known risk factor of cardiovascular disease.
Okay, still not much convincing, but we will have a discussion over it.
Yeah, sure. You
Fine.
can have a look at their work, that is published already. And this is a cohort, that's what I'm telling. This is a strong evidence.
Okay, we'll see about it. Thank you.
Thank you very much for this overview of these studies. I have a comment in general, especially to the last study, you showed this association with nitrate and sulfate.
Yes.
And I just want to throw in here a word of caution. I mean, as we have seen in a lot of studies, actually, there are some components in the organic aerosols that are following actually sulfate very well, and there are other components that actually follow nitrate very well. So what we think, the interpretation, this has been found also in the US, for example, that this association with sulfate, for example. But, it's clearly, in the interpretation, in my opinion, it's not really these inorganics that are really making, the illness or really, is really the cause for this association. But it's actually the correlation with the organics, and the organics are actually the ones that are actually doing the job of being toxic. So I think, I think it's very important to get more information on the organic aerosol to I think have a better link to the the actual molecules doing really the actual association.
No, I just wanted to point out, I don't know whether I mentioned or not, it is a purely model study. So that is the major concern. Okay, we really don't know what would be the exact PM species at that region. It is just a district level emission inventory and others, used, and then finally it's just a model. So there are a lot of uncertainties. That's why these are the evidence. It's just an evidence, but it needs to be confirmed by appropriate cohort studies.
Yeah, thank you very much. My question is very bit more simpler, I think, in that you are looking at the annual mean PM 2.5 concentration as your metric. But then if you think about like a heart disease or the lungs problem, everything, or the asthma, they come very quickly. Like I was talking about like a say 900 microgram exposure for 1 day or 2 days. How does those things weigh in terms of like when you think about the health effect? Do we have hospital data?
So that is what I mentioned, that the cause-specific mortality and air pollution was not associated in India, because cause-specific data is very difficult to get here. But what you are talking about, yes, that can be done through, it is an acute impact. This kind of impact is called harvesting effect. Those people who are supposed to die after 1 month, 2 months, or 3 months because of the high pollution episode, they got this problem, respiratory problem or heart attack, cardiovascular problem, and they died. That's why as is harvested before they die, so that's why we call it harvested effect epidemiologically. This is called a harvesting effect. So this, through time series study, it can be identified, but you need a cause-specific mortality. That is very difficult to get. And even if you look at the classification of deaths in the hospital, you would find 80% are heart attack at that age. So the very high, you will look at that, it is heart attack or some disease related to heart attack. So it's very difficult to get the cause-specific mortality or morbidity. Or I tried one with PM10 and that respiratory hospital admission. That is very, evidence is not so strong. We require more studies on these things. But health data is the major concern in this aspect. We have a pollution data, but not the health.
Okay, thank you. So let me just add to what Dr. Privat was asking. So sulfate means what I feel. Sulfate may not be directly related, but suppose if it is in excess, and if it is helping in leaching out the metals, that means more soluble metals, that can be indirect way of relation between sulfate and, but we have to explore more about it.
Yeah, I need.
Okay, so I think we should.
Just 30 seconds. Actually, what I wanted to tell, sulfate, nitrates, and ammonia, these are going to form soluble salts, and these will have least impact on the health. Because this is nature is producing it. This is sulfate It will form ammonium sulfate, ammonium nitrate, ammonium chloride. All these are soluble things. So it is not going to have a direct health impact.
No, it is
will
not
have
necessary that
impact.
if it is soluble, it will not affect. It
It
not
will
necessary.
impact on the liver. It will impact on the kidney.
Yeah.
In those way, it is required to be investigated. This is my short submission. Thank you.
Thank you.
No, there is no doubt that a cohort is required and more intense study that is required to really answer these questions. These are just observations. These are the just observations.
Okay, okay, thank you. Let us thank the speaker again.
Yeah.
So now may I request Dr. Dilip Ganguly to give the memento as a token of our appreciation. Dr. Santhu Ghosh, please come this side. Okay, just two announcements. One is, we know that we have a next session. It was supposed to be started at 2, but now we'll be starting around 2:15. So whomsoever has not put the presentation, please contact the organizer and put your presentation so that we can start easily. And other thing, we are going to come back around 2:15 or so. So you have a less time for lunch, but we have to maintain the time, we have to do it. Huh? Thank you.